Okay.
Okay. What do you think, Alessandro? What do you think? You can start,
Yes.
because it's
Yes,
9:30.
yes.
And so I recall you again. We have all talks are 20 minutes, 15 minutes of presentation plus 5 minutes for questions and answers. So please be sharp, because we really have no time, no extra time, only 10 minutes after the end of the session we have now. So, so welcome. Thank you to everyone for being here in this very interesting and exciting session. I think one of the best sessions of the meeting. Sure. So, and we have split this, we call you, we have two sessions actually. This session is divided in two blocks, and the second half of the session will be tomorrow at 4:30 p.m. So please connect tomorrow, follow us tomorrow at 4:30. So let's move to the first speaker, is Andrew Melatos. So if you are ready, we can start.
Good, ready.
Hopefully everybody can see the screen. So thank you very much, Alessandro and Jorge, and thank you to the organizers for the invitation and the opportunity to speak during this challenging period. The title of the talk is Mastering the Randomness in Neutron Star Rotation, and the talk will be divided into three parts. The first two parts concern the classic two flavors of neutron star rotational irregularities, so timing noise and glitches. And I'll present two new methods, Kalman Filter and a hidden Markov model, which allows to extract new information about those phenomena. The point there is to study the coupling between the crust and the superfluid of the star. The third part of the talk is, given those data, what can we learn about the stress-relaxed dynamics underpinning pulsar glitches? So just to remind everybody, neutron star rotation is highly regular, but it is not perfectly so. And this picture shows you the frequency derivative of the Vela pulsar as a function of time over about 40 years. And you can see here a lot of different flavors of rotational irregularities. The vertical kind of sudden discontinuities are, of course, the famous impulsive Vela glitches. They're separated by about 3 years. After every glitch, there's a quasi-exponential recovery, which is modeled by those gray curves that you can see there. And then when you subtract those gray curves from the time series, you end up with the residuals, which are shown on the lower panel. And you can see those residuals bounce around, they're wobbly. And that is an example of what we would call timing noise. Now, normally, when we study timing noise, we subtract the fiducial model, like I just said, and look at the power spectral density of the residuals. But the main point of this talk is that actually that time averaged approach is not optimal. The actual time series itself is informative about the dynamics of the star. And to appreciate why that is, one good way is to think about the two-component model of neutron star interiors, which of course is motivated by slow glitch recoveries. And that model has superfluid neutrons, which rotate at an angular velocity omega s, and a rigid crust, which rotates at an angular velocity omega c. And of course, that crust is locked magnetically to the charged species in the star. Now, at the top of this slide, you see the equation of motion for the crust, and there is a similar equation for the superfluid. And the right-hand side contains 4 torque terms. The first term is a coupling term between the crust and the superfluid, which operates on the timescale tau c. The second term is the secular spin-down torque. The third term is a stochastic term, so that's the timing noise, modeled here as a white noise torque, whose correlation function is shown on the second line of the slide. So it's delta correlated because it's white. And then the last term is an impulsive term which occurs at a glitch, and it delivers an instantaneous angular impulse to the crust. And you can see when it's written that way that those third and fourth terms in the first line the stochastic terms, drive the dynamical degrees of freedom, which are the free modes of the star, which are described by the terms in the red box on the left. So you have stochastic driving the free. Okay, now the first part of the talk is about timing noise and specifically measuring the crust superfluid coupling with Kalman tracking. So that stochastic differential equation that we saw on the previous slide is in the same form as a Kalman filter mathematically. A Kalman filter is described by two equations. There's a dynamical equation which tells us how a state vector x, which in our case is omega c and omega s, how that is updated from one time step to the next in the presence of process noise eta I. The second equation is a measurement equation, and that tells us how the timing data, vector y, are related to the state x in the presence of some measurement noise u. The Kalman filter then estimates the sequence of the states x in a two-step process by minimizing the squared error given the data y. Now, the Kalman filter also has an associated likelihood, which is the probability of getting those data y given the various parameters of interest in the problem. We can run that through a Markov chain Monte Carlo and get posteriors on secular parameters like the coupling timescale tau and the spin down torque n, and stochastic parameters like the amplitude of the timing noise sigma. So what does that look like in practice? Here are some tests with synthetic data. So at the bottom left, we have a contour plot of the posterior for two physically interesting parameters, the coupling timescale and the timing noise amplitude. And on the right-hand side, we have the performance of the Kalman filter in terms of its residuals. So the top panel shows you the Kalman frequency minus the true frequency in units of 10 to the minus 10 hertz. The second panel shows you the Kalman timing residuals in units of 10 to the minus 5 seconds, quite low. And the third panel, for comparison, shows you the timing residuals for a traditional tempo fit to this pulsar without including the red noise. And of course, in that case, the residuals are bigger, they're about 10 to the minus 3 seconds. What can we do with this Kalman tool now that we have it? Well, it delivers fast, accurate estimates of coupling timescale tau and the timing noise amplitude sigma. And importantly, it does that for the specific random time series in a particular pulsar. So it's not looking at the time average noise spectrum or anything like that. And that's important because timing noise in pulsars may not be stationary. We can do Bayesian model selection. For example, are one or two stellar components preferred? We can distinguish secular things like glitch recovery from stochastic things like timing noise. And we can ask questions like, are the large breaking indices measured in certain pulsars an artifact of the timing noise? And these matters and others will be discussed by Nicholas O'Neill in the next talk. Now, the second part of the talk is about glitches and specifically distinguishing timing noise from glitches in order to produce a complete glitch catalog. You might remember on the first slide, the Wheeler picture, the glitches are enormous and completely unmissable. But in many pulsars, that's not the case. They're comparable to the timing noise. So how do we separate these two phenomena reliably? Well, we can do it. And one good way is using a hidden Markov model. So a hidden Markov model is an automaton which steps through a sequence of hidden states. The states are hidden because they cannot be measured directly. So for us, that would be the spin frequency of the pulsar. The automaton transitions from one state to the next probabilistically. So due to timing noise, due to glitches, due to secular spin down, whatever. And those probabilities are marked by the letter A on the diagram in red. Also, if you are in a particular hidden state, there is a certain likelihood, L, that you will see the data that are observed at that time step. So for us, that might be the time of arrival of the pulsars. And those probabilities are labeled L, and you can see them next to the green arrows in the diagram. So the hidden Markov model runs through and it estimates the most likely sequence of hidden states compatible with the observations. It also gives you a Bayes factor, for example, for a model containing a glitch at a certain time step versus a model with 0 glitches. And it gives you a posterior on the spin frequency of the pulsar at every time step. So this next slide shows how that works in practice. This is on real data for the pulsar named at the left. The left panel shows you the log of the Bayes factor as a function of time generated by the hidden Markov model. And you can see that at an MJD of about 58,600, there is very strong evidence for a pulsar glitch. At the top right, we see the phase residuals produced by a traditional tempo fit. So before the glitch, they're basically flat, and then after the glitch, they ramp like crazy. And then at the bottom right, we see the posterior on the spin frequency of the pulsar as a function of time, and you can see that it jumps by about 1.5 by 10 to the minus 6 hertz at the epoch of the glitch. So what can we do with this hidden Markov model tool? Well, it's fast, it's systematic, it's unsupervised, and therefore it is well suited to real-time detection of glitches, and that is something currently being implemented. We can ask questions like, what is the false alarm probability of the glitch that has been detected? What is the false dismissal probability of a glitch that hasn't been detected? And that then allows us to speak about the completeness of glitch catalogs. For example, what is the smallest glitch that is detectable given a false alarm probability and a timing noise amplitude? And again, let me emphasize, the hidden Markov model gives us the most likely state sequence for the specific random time series in a particular pulsar. So it's not time averaged ensemble statistics. It doesn't make assumptions about stationarity. And these matters and others will be spoken about by Liam Dunn in his talk on Friday. Now, let me conclude with a little bit about stress-relaxed dynamics of glitches. So the point here is to try and falsify meta models, so agnostic about the microphysics, meta models of the glitch phenomenon in general, which capture the idea of slow accumulation of stress inside the star, which is then released rapidly. So it could be star quakes, could be superfluid vortex avalanches, whatever. And these meta models make predictions about the long-term glitch statistics. To give you a sense of how this works, consider a very simple case where we have a globally uniform stress throughout the star denoted by x of t. And that quantity is plotted in the two panels at the top, x as a function of time. So between the glitches, the stress ramps up linearly in the left-hand panel or wanders randomly in the right-hand panel, but it wanders with a bias towards increasing. In addition, there's a trigger. So that could be crust cracking, could be vortex unthinning, whatever, we don't care. But the trigger operates in two different ways on this slide. On the left-hand panel, we have a state-dependent Poisson process whose rate lambda increases as the stress approaches a threshold. On the right-hand side, we have a Brownian stress accumulation process, as it's called, which is deterministic. So the glitch occurs when the stress reaches the threshold. Now, both of these models can be are controlled by a parameter alpha. Roughly speaking, it's a reference trigger rate divided by the spin down torque. Not exactly, but just for simplicity. And what we can then do is use correlation statistics from the data to try and falsify either of the two models I spoke about on the previous slide. The way we do that is illustrated in the diagram at the left. So what I've done here at the top is plotted the cross correlation between the size of a glitch and the time to the next glitch as a function of alpha. The second panel, cross correlation between the size of a glitch and the time to the previous glitch as a function of alpha. And the third panel, the autocorrelation between the size of a glitch and the size of the next glitch, again as a function of alpha. And of course, all three of those quantities can be measured. For example, for the pulsar J0537, which is discussed here. And for each measurement, there will be an allowed range of alpha, which is shown by the red band in each of the panels. So if the red bands don't overlap for any alpha, like for some range of alpha, then you can falsify the meta model for that pulsar. In this particular case, they do overlap, and that is indicated by the vertical purple stripe, but they don't have to. For many pulsars, they don't, and for some meta models, they don't. So this is quite a powerful technique. Now, what future questions can we ask given this technique? Well, we can predict what pulsars should have strong auto and cross correlations if we can estimate their alpha value. We can ask, do existing data falsify either the state-dependent Poisson model or the Brownian stress accumulation model, or both, which we spoke about before? We can ask questions like, if you double the spin-down torque, do the sizes of the glitches double? Do the waking times halve? Or is it a mix of the two? And all of these are part of a larger exercise to measure the properties of a bulk nuclear superfluid in a neutron star, for example, the vortex pinning forces. And these matters and others will be discussed by Julian Kalman in his talk later today. So, in summary, rotational irregularities in neutron stars are informative. We can track the timing noise with a Kalman filter and measure the crust superfluid coupling. We can track and detect glitches with a hidden Markov model, use that to generate systematically a complete glitch catalog. And then given those data, we can ask questions about the stress-relax dynamics of pulsar glitches, falsify the meta models that I described or others, and measure some properties, hopefully, like nuclear pinning forces. And I guess the overall message of this talk is that the precise, specific time series of the randomness in a pulsar is informative. So please don't subtract it, track it instead. Thank you very much.
Thank you, Andrew, for being time and for this excellent summary of the program you are pursuing on this exciting topic. There is a question by Fabian. Please, Fabian. And then Paul Lasky.
Yeah, thank you very much for your talk, Andrew. I thought that was really interesting. I come at these problems from a slightly more theoretical point of view. So I was just wondering whether there is an effort to connect the timing noise you're describing with some of the physics of the neutron star or the environment it's in. When you say things like secular torque, I imagine you're talking about the sort of the gradual spin down that we see due to the electromagnetic emission. So just wondering if there's a complementary approach to try to understand what you guys are describing as timing noise.
Yeah, that's a really interesting question, Fabian. So we've avoided it in what I described so far deliberately, simply because the point is more to try and falsify some of these simple models. But you're right, you do want to make the connection. People have written about timing noise coming from things like seismic activity, superfluid turbulence inside the neutron star, that sort of thing. All of those processes actually have the property in common that they are not white noise, they're usually colored noise, and specifically the noise that I've assumed in what I described was white, but it can easily be generalized colored. So that's something that's work underway. I think the most interesting thing in terms of tying to the physics is that you can get now a more reliable measure of the sigma, and that is something that has been debated about a lot in the literature. With more reliable measurements of that, I think, may be able to say something, hopefully, about the different causes. And you can also do model selection on different, for example, power law spectra. Other people have done work on that with tempo nest. This is an alternative approach. So I think there's hope, but it's still early days. Yes.
Sorry, if I may, could I come back to that, if that's okay? Is that okay? So, sorry, I can see.
We have another question by Paul.
Oh, maybe I won't. Maybe I'll message Andrew and ask him offline.
Your microphone is switched off.
Oh, sorry. I was just saying I'm happy if Fabian wants to keep going, because I can ask Andrew offline as well.
Oh, okay. Is that okay with the organisers? Yeah.
Yes.
So I was just a follow-up question, because yeah, you're obviously modelling it as white noise. is that a valid assumption? Does that fit the data well?
It's not bad, but it depends on the pulsar. So there's a lot of subtleties there. The white noise in that particular model was a white noise in the frequency derivative. And so then that becomes colored as it passes through the filter of the dynamics when you're looking at the frequency, for example. So you might get, for example, phase residuals with frequency to the -4 spectrum out of a model like this. And that is compatible with some pulsars, but certainly not with all of them. There are some which are f to the -6, as you know, some which are shallower, some which have a turnover. It's a very interesting question, which I won't go into now, but and I don't know the answer, but there's real subtleties about how to interpret those f to the -n power laws in terms of an underlying dynamical model. It's not a one-to-one situation, because when you take a Fourier transform of the autocorrelation function and throw away the phases, you've actually thrown away a lot of information that's otherwise there. So yeah, there are lots of subtleties there, which I'd love to talk to you about. But yeah, the short answer is it is consistent with some pulsars, but certainly not all.
Thank you.
Thank you.
Thank
I
you.
suspect
Thank you very
that
much.
we can move to
Yes,
the,
we can move. We have to move forward. Yes. Thank you. Nicolas
the next
O'Neill.
speaker is Nicolas.
Okay, I'll just bring up my slides.
Okay, go.
Okay, so my name is Nicholas O'Neill. My talk is on parameter estimation for two-component model of neutron stars using a Kalman filter. So what we're interested in doing is probing the internal structure of neutron stars using data on their rotation. So this data comes from pulsars. So pulsars have their bright beams, which swing around as they rotate. And once per rotation, they'll point towards the Earth and we'll detect a pulse. So we keep a list of when all the pulses are. And from that, we can work out how fast it's rotating. We can work out the period, the frequency derivative, anything that we want to know. So pulsars rotate very quickly, sometimes once per second, sometimes faster. But they decelerate gradually over time because they lose energy to their pulsar beams. But they decelerate according to a very predictable, stable long-term trend. However, there are some small random deviations from this trend, and those are what we're interested in looking at. So the main two types are pulsar glitches and timing noise. So a glitch looks something like this. The angular frequency of the pulsar, slows down according to its long-term deceleration trend, and it suddenly speeds up, and then it decays back to the equilibrium trend on some timescale tau. So there are many theories for this, for how this works, but the one that we're interested in investigating at the moment is based on this idea of a two-component model. So the idea is that there are two main components, a hard crystalline outer crust and a superfluid inner core. And since the core is superfluid, there's very little friction between it and the crust. So, so they can rotate somewhat independently, and they can rotate at different speeds. So what can happen is that the pulsar beams, for instance, can cause the crust to lose some of its speed, and it can slow down. But the core isn't directly connected to the crust, so it isn't affected by this, and it ends up going faster than the crust. Right? So this is an unstable situation. So what can happen then is that the superfluid is theorized to contain these things called superfluid vortices, and these are basically little packets of angular momentum, and they can build up in the core, and all at once, a whole bunch of them can decide to move out to the crust and transfer their angular momentum. And this causes the crust to suddenly speed up. Right? And that's one explanation for what we see here. So then we hypothesize that there's a gradual relaxation back to the long-term trend over some timescale tau caused by some interaction between the crust and the core, which wants to bring them back to equilibrium. Okay? So the other kind of deviation from the long-term trend is timing noise. So timing noise is basically sort of a small random walk about the pulsar's long-term trend. Unlike glitches, which are only an occasional event, timing noise is going on all the time. but it's a much smaller effect than glitches. So, but what's of interest to us about this is that these are fluctuations about the long-term trend of the pulsar. So, so it would stand to reason that these could be perturbations of the two components of the neutron star away from their equilibrium. And if that's the case, then we would expect to see the same sort of process that was acting in the aftermath of the glitches acting on the timing noise. Acting on the fluctuations in the timing noise. Right? So we would expect to see that same interaction between the crust and core, causing these sort of fluctuations to die away on a timescale tau. Right? So by looking at all this timing noise data, we can look for evidence of this timescale tau, and hopefully by finding this timescale and measuring it, we can get information about what this interaction is between the crust and core, and this will tell us information about the internal structure of neutron stars. Okay. So based on our observations of glitches and of timing noise, we assume this simple model. So these tell us about how the angular velocities of the two components of the star evolve with time. So C stands for crust, S stands for superfluid core, the omegas are angular velocities, and the I's are moments of inertia. So this left-hand side here, these represent the time derivative of the angular momentum of each component, and these here represent torques acting on each part. So these first two terms, they represent this interaction between the crust and the core that's wanting to bring them back to equilibrium over some time scale. For each component, there's a different time scale assumed. So tau C and tau S are those time scales. And it sort of acts like friction, wanting to bring the two components so that they rotate together. Right? Then there are these ends, and these are torques that are sort of constant in the short term. So they could be from things like the electromagnetic braking torque from the pulsar beams, or from accretion, or from gravitational wave reaction torques. And these represent random torques acting on the two components, and they are there to model the timing noise. All right. And this here just indicates that they're independent, they're white noise processes, and their strengths are given by these parameters, sigma C and sigma S. Okay. And this is just a simplified model that we've used because it models the key things that we're interested in investigating. Okay, so then the next thing is that we want to fit this model to some real pulsar data in order to work out what the parameters are in this model, and that will tell us information about neutron stars. So the key tool that we use to do this is we use a Kalman filter. So I'll explain how that works. The basic idea is that you get your measurements, say these green points, which represent measurements of the pulsar's frequency over time, and then you take your model and you make a guess at the parameters, and you see how well the evolution of the system predicted by the model mimics the evolution of the system seen in the data. Right? So if you pick good parameters, the expected evolution will follow the measurements pretty well. But if you pick bad parameters, it might veer off in some other direction, and that would suggest that this choice of parameters is less likely to be true. Right? So the way a Kalman filter works is basically it assumes that when you have measurements of the system, these are actually the true state of the system plus the measurement noise. Okay, so what the Kalman filter then gives you at the end of its process is it gives you a set of estimates for the true state of the system over time. Right? So that's represented by these yellow points. Okay, so first you make a guess of the true first state. Then you take your model, you make a guess at the parameters, and then you try to evolve forward to the next time. Okay, so you might get this blue point here. It's not necessarily going to end up here because it's a random process because of these random torques, but it should end up somewhere around here. So to make sure that the randomness of the process doesn't cause our measurements to go too far away from our estimates, we combine this, this measurement with this prediction to get a more accurate estimate of the true state. Right? And then we just repeat that. So we evolve forward to the next time, we combine the prediction with the measurement to get a better estimate, and then we repeat, repeat, repeat. Right? So you end up with your measurements and a set of points which represent the expected trajectory based on the model. Right? So what you want to do then is you want to work out how likely it is that that model could have produced this data, given the parameters that we chose. So the Kalman filter is very good at this. It gives you a probability distribution for what the measurements could be, given the expected true state. So all you do is, if you want to work out the probability of the measurements being produced, you just work out, what's the value of this probability distribution at this green point. So you just plug it into this nice little Gaussian formula. In general, it's multivariate, but here I've shown it as univariate just for simplicity. And if you want to know the probability of all these measurements being produced as a whole set, then you just multiply together the probabilities for each point. And that's what we use the Kalman filter to obtain. So it gives us the probability of this of the data being produced given the parameters that we chose, right? We can use that to work out, what's the most likely choice of parameters, right? So before I show you the kind of results that we've been getting, I should say that when we do our analysis, we change from the sort of obvious parameters that are in the differential equation to a different set of parameters. So in the equation, there were the taus, sigmas, and n's, but we introduced these new parameters which have sort of more obvious physical interpretations. So there's R, which is the ratio of timescales and is the ratio of moments of inertia. There's this tau here, which is sort of a combination of these relaxation timescales for each component, and it sort of gives a relaxation timescale for the whole system. And then there's the long-term average frequency derivative, and then this is the sort of long-term average of the difference in angular velocities of the crust and core. Right? So then we tested our method on some simulated data. So we took that differential equation earlier, put in some parameters and generated some data, and then we tried to run our method on it with the Kalman filter to try and work out what the original parameters that we put into it were. So the original parameters that were put in are represented by these black lines, and the sort of recovered probability distributions for the parameters are given by the curves. So the blue curve is if when we try to do the recovery with only 600 data points, and the orange one is for 1200. So as you can see, with more data points, you can get a more precise estimate of the parameters, which is good. That's what you'd expect. So it looks like the method's working here. We get some nice estimates of these parameters. But unfortunately, there is a complication, which is that this assumes that you have measurements of the angular velocity of the crust and the core, which at present is not a realistic scenario. Only the crust is visible because of its pulsar beams. The core is hidden underneath the crust and you can't see it. You can't tell how fast it's rotating. It's possible that in the future with gravitational wave measurements we can, but until then we'll just have to work with only crust data. So we did some simulations and some analytical calculations for the case where we only had data on the crust to see which parameters we'd be able to recover, because possibly with less data we can't recover all the parameters. So this is the sort of simulations we got here. So as you can see, the distributions have changed their shape a bit. Most of the parameters are able to be recovered, except for the lag here, which doesn't really have a peak at all, so it can't be recovered. The time scale here, the relaxation time scale, seems to be well recovered, as well as the noise strength on the crust and the spin down. This one and the strength of the noise on the core and the ratio of moments of inertia, they have slightly funny shape distributions that are a little bit less reliable, but they still produce nice peaks in roughly the correct location. So it seems that this is a promising result. It seems that when we run this on real data, we will be able to recover the parameters fairly accurately, especially the ones that are of most interest to us, like the relaxation timescale, which is sort of the most important parameter. Okay. So then it came to testing it on real data. So the data that we used comes from the Outmost Pulsar Timing Survey, which is reported in this paper here by Lower et al. There's a link to the paper in the source of the data, which is on GitHub. Okay, so the data comes in the form of lists of pulse times, or times of arrival as they're more often called in the literature. Now, our method needs frequency data to run on. So to turn these pulse times into frequencies, we take a few neighboring pulse times at a time, and we work out the average frequency over that period of those pulse times. Right. And so then once we've converted the pulse times into frequencies, we can run a method on the data. And this is the sort of plots that we get. So this is a preliminary plot. It's not quite, published, but this is the kind of results we get. As you can see, the plots show a clear peak in tau, the relaxation. Sorry, in tau, the relaxation timescale. There's a fairly good peak here in the noise strength on the core and on the spin down. These other ones don't have very sharp peaks, so they're not very clearly recovered. But they are, but that's to be expected based on our previous simulations. So this looks like a promising result, but we're not totally confident in it yet. We're still investigating how reliable these probability distributions for the parameters are. We're worried that our method for converting pulse times of arrival to frequencies may introduce artifacts that cause the posteriors to be biased. In the future, when we do further tests, the peaks of these distributions may move, they may widen, or they may even go away. But we're continuing to do more analysis on this problem to determine how to solve this and get the accurate, reliable estimates of the parameters that we want. Right. That's all I had to say. Thank you.
Okay, so thank you very much for your talk, very informative. And of course, questions now, please directly raise your hand or ask a question or write a question in the chat.
Sorry, I can't quite see the chat.
Yeah, I will check the chat if somebody wants to ask a question in case.
Okay.
So this technique, I can imagine that is a technique for analyzing automatically the data will be particularly relevant at the moment in which the big radio telescopes will start taking data. Am I wrong on that?
Yeah, we do have a plan to sort of incorporate this to run on the data in real time. So the Kalman filter is very good for that. Whenever you want to add a new data point, you can just update your posteriors. You can, for the parameters. So yeah, it's very good for that. It's very efficient. It sort of scales the complexity of the algorithm scales linearly with the number of data points, which is a lot quicker than conventional methods. So it's good for that. Yes.
Okay, very good. So any question? Probably people already were following.
I have a question.
Yep. Please go ahead. Yep.
I see this algorithm is complex, and I mean this is a very, very technical. So my question is, how are the theoretical models comparing with this apparatus? Namely, sometimes the technical analysis, that analysis is more advanced than the theoretical models. I mean, how are the theoretical models? They are really such have such complexity.
Sorry, does what have such complexity?
I mean, the theoretical. I mean, are really how much information from the theoretical models can you constrain from this?
The parameters in the model we can constrain using the these posteriors. So as the simulations showed, we can sort of recover these key parameters from the model, but not all the parameters can be recovered. Is that what you were getting at?
Yes, I'm here. I mean, a theoretical model, I mean, with respect to the structure of the star, I mean, how much information from the structure of the star you get from this method?
Right. Well, I mean, if we were able to, if we had estimates of this time scale, for instance, that would tell us information about the interaction between the two layers in our theory. In theory, if there are indeed these two layers and it isn't some completely different mechanism causing the glitches and timing noise. In that case, knowing this relaxation timescale tau would tell us things like the strength of the coupling between the two layers. So the noise strength, if we knew those, that would tell us the strength of the mechanism causing the timing noise, and that would tell us, rule out possible mechanisms that could be causing it. So yeah, it tells us quite a lot about the internal structure of the star. The ratio of the moments of inertia also, that would tell us, how much of the material in the core, like the excess protons and electrons are sort of coupled electromagnetically to the crust. So that would be useful to know. Yeah.
Thank you.
Okay, thanks again, Nicholas, for the nice talk. And I think we have to move to the next speaker, which is the Brabata Deb. So please.
Hello, everyone. Thank you for the opportunity. Hello. So
yep.
My slide is visible?
Yes, perfect.
Okay. Thank you, everyone, for the opportunity to present my work in this session. Before I start discussing what we have done in this work, let me revisit some introductory issues related to this topic. So from the available observational evidences, it is hard to confirm the strength of the magnetic field inside compact stars. This urges researchers to come with some suitable theoretical model that can actually predict the effect of high magnetic field on the physical parameters. And some researchers have even found that the value of magnetic strength at the center is as high as 10⁻19 Gauss. Now, typical values of surface magnetic field for neutron stars may be ranges from 10⁸ to 10⁻13 Gauss. However, for AXPs or SGRs, the surface magnetic field could be as high as 10⁻14 to 10⁻15 Gauss, which are popularly known as magnetar. Now, following strange quark matter hypothesis, several researchers has presented strange quark star entirely made of strange quark matter and cell bounded by strong interaction. Obviously, some electrons are there to maintain charge neutrality. So it will be interesting to investigate the GR effect on the strongly magnetized strange quark stars. Now, let us discuss the origin of anisotropy in a compact star. Ruderman actually predicted in their work that for the compact stellar objects, Newton matter actually interacts relativistically, and the presence of type P superfluid leads to pressure anisotropy. Later, Letian and Bain strongly argued that presence of two or more fluid or their mixture actually can be the possible result of pressure anisotropy. Ferrer et al. Showed that presence of strong magnetic field actually breaks spatial rotational symmetry, which could induce anisotropy within the system. Now, researchers are not agree on the fact whether the maximum mass of the compact stellar object increase or decrease due to the presence of strong magnetic field, which remains an open issue still. And Chu et al. Tried to address this issue by introducing the idea of magnetic field orientation. By the idea of magnetic field orientation, they mean that when local magnetic field are directed toward the radial direction, it is radially oriented, and when the magnetic field are directed. Hello.
So there's some problem with your microphone.
Hello.
Yeah, fine.
Okay, so when the magnetic fields are oriented along the perpendicular direction to the radial direction, say along the theta direction, it is transversely oriented. Chu et al. Also showed that the strength of the magnetic field and its orientation has significant effect on the maximum mass of the stellar object. So in our work, it will be interesting to investigate the properties of anisotropic compact stars by considering effect of magnetic field and magnetic field orientation and its spatial distribution in the 2V equation, which actually not considered by Chu et al. In the present study, we also considered the presence of effective anisotropy arising due to both the local anisotropy of the fluid and the presence of strong magnetic field. And we are going to see that it plays a crucial role for the stability of the spherical symmetric anisotropic and magnetized complex objects. So to describe interior space-time of the spherically symmetric compact star, the metric we use as given in equation number 1, the energy moment tensor for the anisotropic and magnetized matter distribution is given in equation number 2, where the symbols has usual meaning. For example, U contributant mu is the time-like unit vector denoting the fluid force for velocity, whereas P contributant mu is the space-like unit vector in the radial direction. M is the magnetization per unit volume. It is worth mentioning that Ferrer et al. And Sinan et al. Showed in their work that magnetization is at least one order smaller compared to the magnetic pressure, and their effect is insignificant on the physical properties of the magnetized matter. Hence, in this work, we choose not to consider magnetization in the numerical calculation and the presented works. The system density is the sum of the contribution from both the matter and field, here as given in equation number 3. Here rho is the matter density, and depending on the magnetic field orientation, one can see the system parallel pressure, that is the pressure along the magnetic field, reads in the equation number 4, where PR is the radial pressure of the matter. Similarly, system transverse pressure perpendicular to the magnetic field is given in equation number 5, where PT is the matter tangential pressure. Now we can define the mass function of the magnetized star as given in equation number 6, and finally we can arrive to the essential stellar structure equation for the spherically symmetric anisotropic complex star in the presence of strong magnetic field as given in equation number 7 and equation number 8. One can see that in the equation number 8 we have already taken care of magnetic field orientation and the anisotropy too. So here delta is the actually the effective anisotropy coming from due to matter and field both. Now, if one do not consider anisotropic fluid distribution in the compact star, then PR equals to PT, and as a result, anisotropy becomes proportional to B square, which has non-zero value at the stellar core. Hence, anisotropic force also non-zero at the center. And due to this, one problem arises that at the center, hydrodynamic force and gravitational force are 0. But since anisotropic force is not 0, it leads to instability at the stellar core due to non-equilibrium of the forces. So as we have mentioned, this situation can easily be taken care of by considering effective anisotropy due to combined effect of local matter anisotropy and magnetic field. So to close the system of equation and to solve TOV equation, we need a functional form which should maintain the essential assumption given as the anisotropy should be 0 at the center. Hence, the anisotropic force should be 0 at the center, and anisotropy should vary with the position inside the star and depends non-linearly with PR. Also, within the functional form of the anisotropy, we should consider the both effect from matter and the field, and it also important to conclude the effect of magnetic field orientation. Hence, keeping in mind these points, we have modified the well-known Euler-Young anisotropic form as shown in equation number 9, where you can see the orientation of magnetic field, effect of orientation of magnetic field has been taken care. And here dimensionless constant K controls anisotropy within the system, and we choose the value of K well within the permissible range as given by predicted by Silva et al. So to describe Newton star matter, we use a polytopic equation state following Pili et al. As given in equation number 10, where we have used n Pili et al. Used n equals to 1. And to describe Stein's quark matter distribution for Stein's quark stars, we use MIT bag model as shown in equation number 11, where for this study we have choose B, that is Bag constant, equals to 60 MeV per fermion cube. Following Bandyopadhyay et al., we also choose the profile for the density dependent magnetic field as shown in equation number 12, where BS is the surface magnetic field and B0 is a constant parameter proportional to the central magnetic field. Since for Stein's quark star surface density is not equals to 0, we have to modify this functional form, and we have which is shown in the equation number 13. You can see instead of rho, we have used rho minus rho s to ensure surface magnetic field BS at the surface. And for our study, we have chosen surface magnetic field as 10 to the power 13 and 10 to the power 15 Gauss for Neutron star and Sten's quark star respectively. However, note that we found our result is not sensitive with the particular choice of surface magnetic field. So for the sake of presentation, here we have presentation of our achieved result. We have considered a 2.01 Newton star candidate and 1.97 Sten star candidate. And for every paper, note that the left panel shows Newton star and whereas right panel shows Sten's quark stars. So you can see here plot for the matter density, and from the plot you can find that for both the stars in the transverse orientation, as the value of B0 increases, the matter density decreases, whereas for the radial orientation, as the values of B0 increases, matter density increases for all the stars. Same phenomena can be shown for the radial and transverse matter pressure also. You can see for the transverse orientation, with the increase of B0, pressures decreases. However, for the radial orientation, with the increase of B0, pressure increases gradually. We have shown the variation of the system pressures, that is parallel pressure and transverse pressure, and you can see at the center both the pressure has unique value, that is zero anisotropy case has achieved at the center, which is also very clear from the profile for the anisotropy for the both stars for every cases of B0. We have also plotted mass radius curve for the Newton star. You can see from the extreme left panel of the MR curve, where we have shown variation of the MR curve with the chosen value of B0, and you can see for the transverse orientation, at the values of B0 increases, both the mass and radius of the star becomes increases gradually. However, for the radial orientation, as the value of B0 increases, both the mass and radius decreases consequently. And in the middle panel, we try to show variation of MR curve with the increasing value of kappa, that is increase of anisotropy within the system. And you can see as the values of kappa increases, the maximum mass and radius increases gradually. We also showed variation of MR curve for the different chosen value of gamma and eta. This gamma and eta actually comes from the profile of the magnetic field and actually controls how magnetic field decays from the center to the surface. Exact same phenomena can be find from the Sten's quark star from the all MR curve. Like in the left panel, you can see for the transverse orientation, as the B0 increases, mass and radius both increases, and for the radial orientation, as the B0 increases, mass and radius both are decreasing here. And for the anisotropic cases also, mass and radius increases with the increasing value of kappa. We also shown how maximum mass actually changes with the increasing value of central density for the both orientation, and you can see both orientation has significant effect on the stellar objects. The left panel is Newton star and right panel is the Sten star, and as already shown, for the transverse orientation maximum mass increases, and for the radial orientation maximum mass decreases. We also plot the mass with the central matter density, and for the both stars we can find in every case up to maximum mass dm by d rho c greater than 0. This condition has achieved, and which shows stability of the achieved solution or the model. We also plotted adiabatic index for the both stellar candidates in every cases, and find that it is greater than the critical value 4/3 and tells physical acceptability of the solution. So with the appropriate choice of the physical parameters such as B0, eta, gamma, and kappa, we can easily explain the enormously high mass of the lighter object associated with GW 1908-14 event, which has mass ranges from 2.5 to 2.6 solar mass by employing Newton star equation state. You can see that we have easily achieved 3.06 solar mass here through our model. So finally, the highlight of the major results are through our study, we able to show that on the magnetic compact stellar object, magnetic field strength, magnetic field orientation, and anisotropy has significant influence over its physical properties. And through our work also we are able to demonstrate that study of magnetized compact stars, it is essential to consider combined effect of anisotropy due to both the fluid and magnetic field to ensure stability at the center of the star. Also, we are able to solve the long-lasting issue of maximum mass, whether it is increasing or decreasing with the presence of magnetized compact star, and it can be resolved using the orientation of the magnetic field. So that's it. I am grateful to my co-authors, Professor Banibrata Mukhopadhyay and Professor Fridolin Weber. Thank you.
Thank you very much for this nice talk. I have a question.
Yes.
Did you try to estimate the energy of the magnetic field? Because, I mean, when one speaks of magnetic fields exceeding 10 to 18 Gauss, the problem is how do we, from where we get the energy to generate large magnetic?
Yes, we tried to actually estimate that. For the time constraint, I did not able to show the table. In the tabular form, we have shown that the ratio of magnetic energy and gravitational energy is nearly 10 to the power -2 for the compact stars through our model actually.
10 to -2, so it means that you have something of the order of 10 to 52 Hertz, correct?
Yes, yes. So ratio is we achieve is nearly 10 to the power -2.
Because the problem is from where you get the energy to generate such an enormous magnetic field. Okay, there's a question by Jonas Pereira, please.
Yes, I just like to understand something, because you have very high magnetic fields. Wouldn't
Yes.
it be more reasonable, for example, to assume something that's away from spherical symmetry?
Okay, so yes, that can, but we try to consider the magnetic field. We assume that it will not actually deform the stellar structure, and to address the realistic situation, it will be good to consider deformation of the stellar structure in the future work, but it is beyond the scope of this work. We assumed a simplistic model considering spherical symmetry actually.
Okay, but what would you expect in the case of deformations? Would you expect large change, for example, with the maximum mass? Would it shift even more with respect to the critical one?
No, we are not expecting the maximum marks will be shift from what we have presented here, but maybe it will be more realistic if we used non-spherical structure there. And some physical parameters may slightly change, but not the maximum mass.
Okay, thank you.
Okay.
Can I have a comment regarding this question? Banibrata here, his co-author.
Yeah, sure.
Yeah, so basically, if you assume magnetic field is toroidally dominated, first of all, your question is well taken. If field is primarily poloidally dominated, of course, it has to be extremely, for that high field, it would be 19 Gauss at the center. Surface, of course, small. It could be oblate spheroid. But if it is toroidally dominated, it is not necessarily having non-spherical. It will be deviated a little bit. In our work, even 2015, we showed that was exploration of white dwarf, of course. For toroidally dominated cases, hardly 0.95 is the equatorial to polar to equatorial ratio. So in that sense, it is not that bad assumption. Of course, in principle, one should consider radial and polar, both the coordinates. But if it's toroidally dominated case, spherical deformation is that strong.
Okay, thank you. Jorge has a question.
Yes, thank you. Yes, short. The Bowers and Lian model for the anisotropy, it's more that was introduced more for a question of simplicity, because it makes the TOV equation for anisotropy to look like the TOV equation for isotropy case. So, but do you have any idea of any physical realistic model for this anisotropy?
Are you questioning why anisotropy is arising?
Yes.
Okay, so we have already discussed that why anisotropy is arising, since it is a highly dense compact stellar object. So matter anisotropy could arise due to less presence of type P superfluid or phase transition, or due to the ultra dense compact ultra dense nuclear matter there. Also, it is obvious that within the star presence of two or more fluid and their mixture, which could also bring anisotropy. And as I have already mentioned, Ferrer et al. Showed that strong magnetic field could bring anisotropy within the system also. So here we have considered both the anisotropy due to matter and due to the presence of magnetic field.
Okay, a final question maybe by Balibrata.
No. I forgot to lower my hand. Sorry, I was just trying to comment.
Yeah. Okay, so it was very interesting, and thanks again. And okay, I think we can switch to Jacopo.
Yes, hello. So let me share my screen. Okay, can you see the full screen of the slides?
Yeah, perfect.
Okay, nice. So I'm Jacopo, I'm a PhD student at the University of Florence. And so I will present today some works that we have been doing on some quasi-universal relations regarding the magnetic deformation of neutron stars in general relativity and in one of its extensions. So let me start with this last part, its extensions. So why should we study alternatives or extensions to general relativity? So that can happen for a variety of reasons. So from the theoretical point of view, you have the fact that the Hilbert-Einstein action, which is the action of GR, is not the only possible one. So you can have, let's say, infinitely many different actions for a theory of gravity. Then, of course, no consistent theory of quantum gravity through general relativity exists. And then from the observational point of view, you have the fact that roughly 95% of the universe has a matter energy content which is unknown. And this problem can be studied from two different points of view. So one is to introduce a modification to, let's say, particle physics, that is dark energy and dark matter, while the other point of view is to modify the theory of gravity. And so the most simple and probably most studied extension of general relativity are scalar tensor theories for a variety of reasons, and they are the easiest way. So if you consider the action of GR, which is only the integral of the Ricci scalar, and the action of matter, you can modify it with in scalar tensor theories in this way. So you add the scalar field, which is said to be non-minimally coupled in this way. So you have this product. And then you have an energy of the scalar field with a potential and the free function, which is this omega. You can study scalar tensor theories in two different frames. So this is a Jordan frame, and then you can make a transformation, a conformal transformation to the Einstein frame, which is this one. And they have different forms, so and different features. So in the Jordan frame, you have a non-minimal coupling, which means that the equations of gravity are more complex, let's say. However, the weak equivalence principle holds because in the action you have no scalar field. And this means that MHD, magnetohydrodynamics equations in this frame are easier to write. So they are the same as in GR, basically. On the converse, in the Einstein frame, you have easier equations on regarding the metric, while you have more complex equations regarding the action, the MHD quantities. And just a note, so instead of the coupling function omega, which I showed earlier, we usually use a different coupling function, just renaming it. It's called A. And a common choice is to use this function of the scalar field as an exponential with two different parameters. And so you have an alpha 0 and beta 0 parameter. And particularly important is this beta 0 parameter, which regulates the strength, let's say, of the scalar field in the highly nonlinear regime. So let's jump to what we did. So we use the XNS code. This XNS code is a code which solves the full Einstein-Maxwell system of nonlinear equations for rotating magnetized neutron stars in a let's say, numerical approximation called the extended conformally flat approximation. So it makes the assumptions of stationarity and axisymmetry. And what we did was to extend this code to include the presence of a scalar field, so to study scalar tensor theories also, and also to work with any tabulated equational state. And so we found, as I will show later, some interesting results regarding real equations of state. It works in isotropic coordinates. So you have just, let's say, three functions of the metric, which is the lapse function, the conformal factor, and if you have rotation, the shift vector. So we decided to solve all fluid and electromagnetic equations in the Jordan frame, because as I said earlier, it is easier in this frame, and the metric and the scalar field equations in the Einstein frame, because it's let's say, the most natural and easiest way. And then we convert from one frame to the other as needed. So just to give an idea of how it works with a iterative solver. So you start with the TOB equations with a scalar field if you want. So spherically symmetric, non-rotating, unmagnetized neutron stars with the scalar field. You start by solving the equation of the conformal factor, then of the lapse function, then the scalar field if you have it, and then you solve the equation of the magnetic field. So XNS works for both toroidal and poloidal magnetic fields, actually also for twisted torus configurations, but we did not study them yet in scalar tensor theories. So in the toroidal case, you have an equation to solve for the enthalpy, let's say. However, while in the poloidal case, you have an equation for the enthalpy and an equation for the phi component of the A vector of the magnetic field, which means solving the Grad-Schaffner of the equations, basically. Then, once you have found everything, you can calculate the new hydrodynamic electromagnetic quantities and you check convergence. So let's jump to some results. So what we did was study the magnetic deformation of many models of static and axisymmetric neutron stars. So the quadrupolar deformation of neutron stars can happen due to a variety of reasons. So for example, you can have crustal deformations or a magnetic barrier, which can lead to the formation of mountains. You can have a misalignment between the magnetic and the rotational axis, which leads to a time-varying quadrupolar deformation. You can have an instability due to the presence of a strong toroidal component of the magnetic field, and you can have starquakes, which can excite oscillation modes, which well, some of them are unstable. All of these can result in the emission of gravitational waves, both continuous or in bursts, which could be detected. So in particular, what we studied was the magnetic deformation, which is defined as it's usually called the ellipticity. So it's the difference between the two principal moments of inertia of the neutron stars, normalized to one of them. And we studied them in the low magnetic field regime. While by low magnetic field, I mean low with respect to the, let's say, to the numerical, to the maximum numerical values, which we can study with our code, which means less than 10 to the 17, let's say, Gauss, which is still very high, can be very high, of course. So in this regime, it was proved basically that you can study the ellipticity by expanding it with respect to the maximum magnetic field of the star, or with respect to the ratio of the magnetic energy to the binding energy. And these two coefficients, which appear on the front, are called the distortion coefficient, and they depend on the mass of the neutron star in general. While in scalar tensor theories, they also depend on the beta zero parameter, which I showed earlier, which regulates the strength of the scalar field. So here is a plot of these two coefficients for a purely poloidal field or purely toroidal field. In the case of the polytropic equational state, in this case. And the red curve is general relativity, while all the other curves are the beta zero parameter, which is lower, so higher in magnitude. So the lower it is, the stronger is the scalar field. As you can see, basically the effect of the scalar field is to strongly reduce the distortion coefficients and thus the deformation of the neutron star. which means that the scalar field acts as a stabilizer for neutron stars by making them more spherical, basically. What we found was that these two coefficients, CB and CH, have a very simple can have a very simple expression in terms of the mass of the neutron star, of its radius, and of the scalar charge in scalar tensor theories, where the scalar charge is basically, again, let's say a measure of how strong the scalar field is inside the neutron star. And so what we did then was to ask ourselves whether all of this holds for both in general relativity and scalar tensor theories for any equational state, also for, as I said, tabulated equational state. So we did the kind of the same study for a selection of 13 different equational states, most of which are allowed by observational and nuclear physics constraints. So this is a list here of the names of the equational states which we studied. So 12 of them are, let's say, tabulated, while one of them is the polytropic equation, which I showed earlier. So these 12, the first 12 of them are allowed by observational and nuclear physics constraints. And 2 of them, which are the SQM1 and SQM2, are equational state for strange quark matter stars. So this is just to give an idea what these equational states represent. So you have the mass radius diagram with where you can see the different maximum masses that they achieve and different range in radii. And in this case, on the right-hand side, you see the same thing, but calculated in a scalar tensor theory with this parameter, which means a strong effect of the scalar field. And you can see all these points here and here, where basically the derivative of the curve changes, and are points of departure from GR. So let's say up to this point, it is like general relativity, and when the scalarization occurs, you have a strong deformation of the curve. And of course, the radii and the masses that can be obtained can be much, much larger than in GR. So this work that we did may be useful to disentangle the effect of the equational state and of the scalar field, because the effect of changing the equational state can be similar to the effect of simply adding a scalar field, like a change in the maximum mass or maximum radii. And moreover, it can be helpful to infer information on the internal magnetic configuration of neutron stars, which is mostly inaccessible. So in particular, we computed the distortion coefficients for many models, where many means something like 60,000. So both magnetized and unmagnetized in general relativity, in scalar tensor theories with these parameters, for 12 realistic equational state, and for the polytropic, just to compare it with our previous results. And we perform what is called a principal component analysis, which is let's say a very, very simple machine learning algorithm, which is used to discover correlations among the parameters. And so the parameters that we choose are the Komar mass of the star, the circumferential radius, and in scalar tensor theory is also the scalar charge. So the most basic, let's say, quantities. And we studied the distortion coefficients CB and CH, which I showed earlier, and also a new distortion coefficient introduced here, which is the same as CB, but instead of the maximum magnetic field, you have the surface magnetic field, which is, of course, more accessible by observations. And what we found are several equations, which are very simple in terms of these 3 quantities, which are independent of the equational state, and that's the name quasi-universal, and only slightly depend on the magnetic field configuration. So in this diagram, which I show here, you can see on the y-axis the computed distortion coefficient from the simulation. On the x-axis, you have the approximation given by the PCA algorithm, which is given, for example, in this case, for the CS coefficient, but it's very simple formula, so just the power law of the radius and of the mass. So a line CS equals to CS PCA. So this straight line, which is the dashed line here, means a perfect approximation. As you can see, the errors of all our models, which are these points here, are usually very low, so just some percent. So the approximation is very, very accurate in general relativity. In scalar tensor theory, we studied the difference with respect to GR, which again has a very simple approximation, but just by including also the scalar charge, and still has a nice, so it's still a nice approximation with slightly larger errors. So all the different colors are equations, different equational states shown here. As you can see basically no correlation among the equational state and these quantities. So they are mostly independent on the equational state. Here are not shown the two strange quark matter and the pole 2 equational state, because in that case we did a different studies because they are very different. They have a very different behavior from all the other equational state that we found, and we found that the error when using these approximations is slightly larger, so something on like 10% to 50% more or less, but still not huge. And we found similar relations also for the other distortion coefficients. Then another thing that we did regarding the scalar field this time is to study this quantity here. This quantity is a ratio of two quadrupoles. So on the top you have the what we call the trace quadrupole. Is basically the source of scalar waves, because in scalar tensor theories you have a different kind of gravitational wave, which is given by the deformation of the scalar field. So it's and has this source. Instead, here you have the mass quadrupole, which is the usual mass quadrupole, which is the source of tensor waves, also with the addition of the energy contained inside the scalar field. So this fraction is the fraction of the energy lost in quadrupolar waves in scalar modes with respect to tensor modes. So if it is higher than 1, you have more energy in the scalar modes. If it is lower than 1, you have less energy in the usual tensor waves that you have in general relativity. And we did the same thing with the PCA algorithm. So we found an approximation of this quantity S, which has a very simple relation, and is extremely accurate, both in the poloidal and toroidal field case. And an interesting thing that you can see is that, as you can see by the coefficients, so they are practically the same. So it's the same approximation in the poloidal field and in toroidal field case. So what we think is that this may be a, let's say, universal quantity, which does not depend in any case on the magnetic field configuration of the neutron star. And then all these relations that we found can be used, for example, in a variety of ways to infer, for example, the strain of gravitational waves, in this case in general relativity, from, for example, by pulsars in the galaxy in a equational state independent way. So you have the strain is proportional to the ellipticity times the moment of inertia. And the moment of inertia was found to have a quasi-universal relation by Bremer and Zola that depends only on the radius and mass of the neutron star. So basically the strain is the function of the mass, the radius, the magnetic field, for example, the surface magnetic field by using the CS coefficient for the ellipticity, the distance, and the rotation frequency. And so, for example, in this diagram, which is a preliminary result that we have just found, you can have an estimate of the strain of pulsars in our galaxy, for example, and compare it to the sensitivity of current gravitation and future gravitational wave detectors. So the green lines are the sensitivity of advanced LIGO for different observation times, and the black lines are the same sensitivity lines, but for the Einstein telescope. While these points are basically pulsars taken from the ATNet catalog, where, for example, the radius, so to calculate this thing, the radius must either be known by observations, or you can calculate with assuming an equational state from the mass. Since the radius is very difficult to obtain, what we did here was to obtain it from the mass using the two most extreme equations of state, which are these two shown here. However, as you can see, the difference is in the distribution is very minimal between the two. And here you can have an estimate, for example, of the fraction of pulsars which are detectable with the different telescopes. So another thing which you can do is to calculate the CS coefficient given the mass and the radius of a neutron star with a PCA approximation, and in another way infer it by measuring the ellipticity and the magnetic field. So if you have that the inferred number is less than the calculated number, you must have a toroidal component. That is because the CS-PCA component was calculated assuming a purely toroidal field. So if you have a toroidal component, the two components mix and reduce the observed ellipticity. Instead, if you have the opposite, there is
you should conclude, Jacopo. You should go
sorry.
to conclude. You should conclude.
Sorry. And so let's say you can have this with the CS component, you can infer the configuration of the component of the toroidal component, and however, with the other two CB and CH coefficients, you can have a very simple relation to quickly compute the deformation strain without going through a few numerical simulation. And so that's all. Thank you.
Okay, thank you. Maybe we have time only for one question. If any, there is one who is, please, Jonas.
Yes, Jacopo, I just wanted to understand something regarding the fields, magnetic, poloidal and toroidal, because normally they are individually unstable. Is it the same in your case? And shouldn't you use a combination of them to make meaningful calculations and compare with observations?
Okay, so yeah, that's a fair question. You're right. The two single components are unstable. So the real configuration should be a mixed field. And however, let's say in our code, the twisted torus configuration is, of course, you can study it, but it's a bit tricky because of you have stable configurations only for particular choices of the surface currents. And however, by doing the two most extreme calculations, we believe that we have given let's say the most extreme values of the magnetic deformation that you can have. So while if you have a mixed component, you expect to have something which is in between the toroidal and poloidal components. But indeed, it's something that should be done in the future.
Good.
Okay,
thank you, Jacopo. Okay, we can move forward to the next speaker. It's Paul Lasky. So you can interrupt your sharing.
Yes. So yeah.
Sure. Okay. Paul. So we can. Okay. Please.
Thank you very much. Let's just get into full screen mode. Okay, wonderful. Thank you very much to the organizers for organizing a wonderful session. It's nice to be able to attend these meetings, even though we're not allowed to leave our country at the moment. So I'm going to tell you a little bit today about a proposed gravitational wave observatory that we've designed. And we call it NEMO, which stands for the Neutron Star Extreme Matter Observatory. And this talk really is on behalf of a very large collaboration of people. So we have the OzGrav network down here in Australia, where we're working together on all aspects of gravitational wave astronomy. And one of our key projects over the last couple of years has been combining our expertise in data analysis, in astrophysics, and in instrumentation to design what we think is really an optimal future observatory, sort of a 2.5 generation detector, if you will, which is designed to bridge the gap to get us to third generation detectors in terms of the uncharted territory with technology development that hasn't really taken place yet, to get to things like Cosmic Explorer and Einstein Telescope. But at the same time, to get some dedicated science out, and that dedicated science is really to look at neutron star extreme matter. And I'll talk about all of these various aspects as we go through, but that's sort of the punchline of the talk, is that this is a detector design for doing extreme matter, but also for developing a pathfinder detector for full third generation interferometers. So we have this lovely, beautiful graphic from the amazing Carl Knox, who's an artist in residence, I guess, for lack of a better term, within Osgrav. He's located at Swinburne University. And he has actually created a number of graphics for us. And I'll show you this one, which is also something that's appeared in a recent review that I wrote with my PhD student, Nikhil Saran, which is now fully published. And this is on post-merger remnants. And so this really articulates sort of the design goals for NEMO as well, because what we're looking at here is the evolution of binary neutron star mergers through the merger and into the post-merger phase. So typically we're used to seeing the in-spiral phase, and this is depicted in scene A here. And then you have this merger. There's some artistic license here, and we've gone with blue being a cold color. Just ignore the physics. This is very much artistic license. But the blue represents here the cold state of neutron star matter. But during that merger phase, this thing heats up, and it can go through a number of pathways. It can either collapse to form a black hole plus torus system and launch a GRB, or it can form a stable or a metastable neutron star. And that metastable object, or stable object indeed, depending on the masses, that can emit really, really strong gravitational waves. And the whole point is here that post-merger remnant is incredibly hot. And if you're to have any kind of sort of phase transitions in neutron stars that are temperature dependent, then this could be one place in which they would appear. And you can actually try and measure that by detecting gravitational waves from this post-merger remnant. I'm not going to talk too much about the rest of this diagram in this talk, but it's very much encourage people to read the review. You can analyze these sort of post-merger remnants in terms of long-term evolution through electromagnetic observations with X-ray, radio, optical emission, et cetera, et cetera. But we've observed binary neutron star mergers in the past. So let's talk a little bit about what we did see for the most famous of all of these in GW 170817. So this was the first binary neutron star merger observed with the LIGO Virgo detectors. The top left shows the spectrogram, the time frequency map of the gravitational wave signal with the beautiful and famous characteristic chirp just for the last 10 seconds of the in-spiral. And of course, doing parameter estimation on these signals, you can measure the masses of both the two neutron stars, and this is what's shown on the left here, so you can get the primary and the secondary mass of the neutron stars. It turns out 170817 was kind of a garden variety neutron star system compared to our double neutron star systems that we observe in the galaxy. That's not true of the other binary neutron star system that we've observed with LIGO Virgo, but I'm not going to talk about that today. But one thing that you can really measure is this tidal deformability parameter. And so this is a measure of, how deformable, or in other words, how squishy your neutron star matter is. And so it's an indirect measurement of the equation of state of nuclear matter. Now, this is the posterior distribution, the two-dimensional marginalized posterior distribution for those tidal deformability parameters of the primary on the horizontal axis and the secondary, so the most massive and the least massive neutron star. And you can see that they're not overly well constrained. You can get some interesting constraints on sort of this parameter that's less than a few hundred, give or take. That rules out some of the really more stiffer equations of state. And so you end up with neutron stars sort of being confined to, less than 13 or 14 kilometers or something along those lines. Obviously, the more systems like 170817 we measure, the better constraints we'll have on parameters like this. But you can really start to see that this measuring that in-spiral phase of the binary neutron star merger can measure the tidal deformability. But I mentioned before that when these two neutron stars merge, we end up with some kind of post-merger remnant. Well, what was measured, or we potentially end up with some kind of post-merger remnant, perhaps a black hole, perhaps a neutron star remnant. What did we measure for 170817? And the answer is absolutely nothing. Okay, so despite looking as part of the LIGO and Virgo collaborations, we looked very, very hard, and there's two papers, one in 2017, another in 2019, where the LIGO collaboration itself looked very hard for post-merger remnants. But what you can see, the back left-hand plot is really a very confusing representation of these searches. The top right-hand plot is a much better representation. The different colors represent different search algorithms, essentially. So it's not too important on what they are. You can see HMM there is the hidden Markov model, and Andrew Melatos talked about that early on in this session today for a very different purpose. But you can see there's a bunch of different algorithms. And the takeaway message from this plot is no matter what the gravitational wave frequency would have been, whether it be anywhere from 500 hertz to 2 kilohertz, the actual sensitivity of our interferometer only went out to about 1 megaparsec. Now, in truth, this 1 megaparsec is nowhere near enough. The 170817 was located around about 40 megaparsecs. So we're in fact a factor of about 40 away in terms of the strain sensitivity for the gravitational wave interferometers. So you've got to do a lot better than LIGO Virgo in the second observing run to be able to measure a system like this, or the first or second observing run, to be able to measure a system like this. So that leads us through to talking about, what is next in terms of gravitational wave astronomy. And what I'm showing here is a plot of the characteristic strain. So the gravitational wave strain is a function of frequency for the different interferometers that we currently have in black. So you can see that the dashed black curve shows the advanced LIGO around about the 0.3 sensitivity. It gets better going through to the design sensitivity. And then you've got A+ design sensitivity, which is mostly funded, mostly minimal technology risk to get towards building a detector like that. It uses the same cavities. It uses everything that already exists in advanced LIGO. And you can see you get a factor of sort of 3, 4, maybe 5 better in sensitivity overall. That does not get you through to post-merger remnants, and I'll show you that very shortly. But then you've got to jump. So A+ design sensitivity, perhaps that's going to be circa 2024, 2025, sometime around the middle of this decade. But then there's a jump towards Cosmic Explorer and Einstein Telescope, which really are detectors that are being designed for the mid-2030s and potentially even late 2030s. These are not funded. They're very much uncharted territory in terms of that technology development. There's a lot more research and development on the instrumentation side to get us to that factor of 10 improvement in sensitivity that we really need to be able to detect post-merger remnants. But this is where we envisage that NEMO, or a NEMO-like interferometer, can step in. So this is the design sensitivity curve for NEMO. Sorry, there's a typo on the slide. This is an old graph where it says it's called OzHF, which used to stand for Australian High Frequency, but now we call it NEMO. On the order of $100 million experiment compared to on the order of $1 billion or a few billion for Cosmic Explorer and Einstein Telescope. Dedicated science goal is to detect neutron star post-merger remnants, a little bit of the in-spiral as well, but really at the same time, it's a technology development tool for full 3G detectors. So what you can see from this sensitivity curve is it's a very different shape to the Cosmic Explorer type and Einstein Telescope detectors, and also to LIGO and advanced LIGO. You can see we've dumped a lot of effort into getting sensitivity up in this high frequency regime, so up around 1 to 2 to 3 kilohertz. Whereas we've really sacrificed low frequency sensitivity, just completely thrown it away. Okay, this is what makes this interferometer cheap. Cheap in the order of $100 million, 100 million euros, depending on the currency you want to talk in. But this is what makes it cheap, because that low frequency seismic noise mitigation is really difficult. But if you dump all of your power and don't care about some of those low frequency problems, then you can actually get very high sensitivity up in that kilohertz regime for a fraction of the cost. Okay, so what does this do? This is just sort of stripping back that last plot, and I should mention that this is all presented in a paper that includes the full author list of the OSGRAV contributors. So Kendall Ackley starts with an A and then a C, so she gets the first authorship. But there's the full OSGRAV cohort of authors. We couldn't split it out. So this is the sort of detector design. Again, you can see that the Cosmic Explorer and NEMO have very similar sensitivities up in the 1 to 2 kilohertz regime, but we think we can get there a lot earlier and we can get there a lot cheaper. So what does this get you in terms of science? We know that binary neutron stars, when they in-spiral, they come in through the frequency band. So they start at low frequencies when they're at large separations. They come in through this frequency band before they merge up at high frequencies, up in the kilohertz regime. During that late in-spiral late in-spiral process, that's where you get this tidal deformability measurement. How do we do? Not too bad at all. So what we're showing here, the numbers on the left show the binary neutron star rates that you get when you've got two A+ detectors and when you've got two A+ detectors plus a NEMO detector. So we showed in a paper written by a PhD student at Monash, Francisco Hernandez Vivanco, a while ago, that to get equation of state information and to be able to stack up neutron star equation of state information using in-spirals, using this tidal deformability, you really need signal to noise ratios above around about 20. So what we did was we said, okay, well, how many of those are we going to get in a given year? And the answer is around about 44 if you have 20, if you have two A+ detectors. Whereas if you've got two A+ detectors plus a NEMO detector, you get around about 61. So you get this modest improvement just in terms of the sheer number of mergers that you'll detect above a certain signal to noise ratio up in that sort of regime where the late in-spiral is important. What we're showing on this bottom right plot, though, is the improvements that you get on the equation of state. So we did these signal injections with and without NEMO. Without NEMO, you can see the two A+ detectors is the equation of state. The combined constraints that we get is shown in gray. And when you add NEMO, you can see the combined constraints are shown in green here. So, you know, just to sort of put some numbers on it, if you want to try and measure the TOV mass or the maximum non-rotating mass of neutron stars, then you get about a factor of 2 improvement in that MTOV. Now, if I was to be honest, I'm not going to go to the government and argue for $100 million just based on getting a factor of 2 improvement on MTOV. The power of NEMO really is in this post-merger phase. So what you can see on this, on the left here, and this is some work that was driven by Meg Millhouse at Melbourne Uni. Meg did some simulations for us where we injected signals into networks of just A+ and into networks of A+ and NEMO. This is post-merger gravitational wave signals now. So you can see that the merger happens at 0 milliseconds here. This is just a windowing artifact, the fact that there's non-strong gravitational waves there, and then recover that signal with this Bayes wave algorithm, which does an arbitrary signal recovery, a non-parametric signal recovery. And what you can see is for a fiducial 1708-17-like signal, so at 40 megaparsecs, give or take, you can see that we don't recover just with A+ a signal like this at all. On the other hand, when you add NEMO, because of that extra high frequency sensitivity, you really do get a really good match, and you can trace the phase of the gravitational wave signal throughout its evolution, and therefore measure, you know, hot equation of state parameters depending on how you parameterize your signal and things along those lines. And that's, of course, a very open question and an interesting research question in and of itself. The right-hand plot here really is the take-home message here, though. What we're showing here in blue is if I just have 2 A+ detectors, this is the average number of detections per year on the vertical axis for a post-merger signal. And this is just saying, okay, I need to detect post-merger gravitational waves with a signal noise ratio greater than 5. The uncertainties here, so the size of these lines is just the uncertainty on the rate of mergers in general. Okay, and so with 2 A+, then you get on the order of 10 to the -2 to 10 to the -1 detections per year with a NEMO-like detector. With 2 A+ detectors. The horizontal axis just shows different equation of state parameters and associates the dominant post-merger frequency. And so you can see it's pretty consistent, independent of the equation of the unknown equation of state. What's shown in black, though, is what happens with this average number of detections when you have a NEMO detector in your network. So what you can see is this pushes that average number of detections up to on the order of 1 per year. So rather than having to wait for 10 years to be able to detect anything like we expect to have to wait with an A+ network, now with the inclusion of NEMO, we start to get on the order of 1 per year, perhaps even up to a few per year, depending on that unknown rate. Of course, there's all of the extra science that you get with this, and you know, just some throwaway lines here. Of course, things like equations of state, you can measure using that. There's been some recent work showing that if you can measure post-mergent remnants, and you get some independent constraints on cosmology, they independent from the in-spiral phase, and that sort of helps you break some degeneracies. And of course, you know, understanding gamma ray bursts in general, you get a lot of information from measuring both the in-spiral and the post-merger phase. Of course, all of that is just the gravitational wave detectors themselves, and this is not to mention anything about the multi-messenger astrophysics that you might be able to see as well, which I won't go into any detail about today. Okay, so it's all very well to design an experiment that says, well, here is a fiducial sensitivity curve, and this might be a little bit the wrong audience today, but this is just to show that we do have preliminary designs for understanding how an experiment like this would work. And this is actually, you know, the instrumentation team within Nosgraph has done a fantastic job of setting this up and really understanding all of the potential noise sources. And I'll go into a few in a second. But the technology required here, the only real challenges associated with going from an A+ style detector to a NEMO is just what happens when you really pump up that input power and the circulating power in your arms. So you can see you've got sort of something like 4.5 megawatts of power in your arms. It's still a 4 kilometer interferometer. That's very much negotiable. You can make it a 2 kilometer, you can make it an 8 kilometer. That comes down to a cost benefit analysis. The cost of these things scale almost linearly with the length of your arms. We use, you know, 7 dB of quantum squeezing, which has absolutely been proven in the lab. So we don't think that that's any problem. But the whole point of this is the way you get this cheap is to neglect that low frequency isolation, okay? When you increase the power, you have to go to, you know, you've got very heavy test masses. You need to cool those down to 123 Kelvin. You have to change the wavelength of the laser, et cetera, et cetera. A lot of this is also what you're going to expect to see in the full 3rd generation interferometers. And that's why we think that this is a great testing ground, a high power optical facility for those full 3G interferometers. Just to show you, this is sort of some of the modeling now of all of those underlying noise sources for what you would get with a NEMO detector. And so you can see that, you know, you have the main sources of noise is really this quantum noise, and it's the quantum noise almost throughout. So whereas normal LIGO interferometers, or the current generation of LIGO interferometers, dominated at low frequencies by this seismic noise, and the seismic, we're sort of throwing away all of that. You've got all of these thermal violin modes, which you actually see in LIGO and things as well, so they're not a surprise. We don't think there'll be a problem, but that's also got some extra modeling to do as well. So that's our sort of very fiducial preliminary design for what NEMO would look like, and some of the science it can do. There's, you know, a lot more work going into this that I'm sort of very much skimming over for the benefit of brevity. But I do want to mention just very quickly in a neutron star session that one thing you can do with an interferometer is a thing called detuning. And what that means is basically you have this signal recycling cavity, where I just realized I've spelt that recycle. I don't know what I've done there. You can have a signal recycling cavity, which basically changes the sensitivity of the instrument over certain frequency bands. So here's the standard NEMO curve in red, A+ in blue, but you can start to design things like this. And so you get much better sensitivity at some frequency. Here it's around about 1.5 kilohertz by really tuning the length of your signal recycling cavity, okay? There's some science case there for the post-merger remnants, but of course you need to understand there's a trade-off between bandwidth and sensitivity, and that's sort of an ongoing area of research. But one thing I do want to mention is that with these kinds of things, with detuning your cavity in this way, what you can actually really start to probe is continuous wave signals. And so you could actually start to probe you know, whether it be mountains on isolated neutron stars, or whether it be through torque balance, various things along those lines, you can actually start to dig really deep into isolated neutron star continuous waves. And so here's just on the left here, I've just made a plot where I've shown if with 2 years of observation with A+, with a fiducial NEMO and with a detuned NEMO, that you can actually push down to 10⁻⁹ in the ellipticity, which is in some sense a magical number. And I can see that I'm getting the hurry on, so I will leave it there and say thank you very much.
Thank you, Paul. Very, very honest talk. Extremely honest. let me see if there is any questions. Not yes. Andrew.
Thank you, Jorge. Thanks, Paul. Very interesting talk. The detuning you mentioned at the beginning was planned for advanced LIGO as well. Didn't in the end happen, but you know, it was part of the discussion. Do you have a sense for how long it would take to kind of do the detuning? Like, is it something that can be done on the fly, or would the interferometer have to go down for a couple of months, kind of thing?
Yeah, look, it's talking with people like Dave Ottaway and Johannes Eichholz and these folk and Vaishali, Ajan, we've really tried to ask the question of, can you do this on the fly? Suppose you got a gravitational wave in spiral detection with A+, and you've got 90 seconds to detune. Can you do it? They reckon it's really a pipe dream, and the answer is no. So that dynamic detuning doesn't seem to be possible, but it's something that people are very, very interested in exploring. So it looks like you have to shut it down, and you know, I think it's on the order of days to weeks to actually do it in the simple case if you set it up right. So I don't think it's a significant amount of downtime, but it's not something that you would just continually bring it in and out of a detuned locked configuration and back to a normal
Quick last question. Quick question by Jonas.
Yes, Paul, I just wanted to understand something. You showed some mass radius relations regarding cold stars, but the NEMO will focus on the post-merger. How do you go from hot Newton equations of state to cold ones? Because they could be totally different.
Yeah, absolutely. And that's one of the really exciting things in my mind. So the mass radius diagram that I showed was just for the in-spiral phase. That was the parameter inference that we get just looking at the in-spiral only. Absolutely, if you get, you know, and there's beautiful papers by Andy Bauswein and collaborators showing that if you can, you know, that's the way to detect phase transitions or something exotic happening in the core. You can predict the in-spiral, the post-merger fundamental frequency, and it's actually different, you know, than your home and hose. You've got something there that's really fascinating. So the mass radius diagram I showed was for the cold equation of state. We haven't looked into any details of what you'd be able to get in terms of those first or second order phase transitions that Andy and other people look at. But absolutely, that's, you know, getting both is key to doing a lot of science here.
Thank you, Paul. Thank you very much for your talk and your answers. Let's move fast to the next talk. We are already almost 7 minutes late. Please, Melissa, you can share your screen.
Okay, hopefully you can see that and you can also hear me.
Yes, yes, yes.
Okay, awesome. So, hello everybody, I am Melissa Mendes, a PhD candidate at McGill University. Today I'm going to talk to you about our research on probing the dense matter physics of neutron star cores with transiently accreting neutron stars, case study of source MXB 165929. So, as you know, neutron stars can be roughly divided into a crust surface and a core area. And the deeper you get into a neutron star, the more dense region you approach in it. And we get to the first open problem of neutron stars, which is what is the composition of the core? So we know it should be some protons, it should also be some, like mostly neutrons, but some protons, but they could also be strange quarks, could be hyperions, could be free quarks. So we don't really know what's going on there. And the other thing we don't know is how to model the superfluidity and superconductivity that's inside the core of the neutron star. So we hope and we expect to see some Cooper pair formation of neutrons and protons, but we don't really know how to describe the amplitude of this gap, so the energy that is necessary to do that, and when it starts and when it ends in terms of the density of the star. So to shed some light on this, we have this research, and we're specifically studying transiently occurring neutron stars, which are basically neutron stars in a binary. So they have a companion, which could be a white dwarf, it could be a main sequence star, and they periodically accrete matter from this star. So so they periodically accrete matter, but they also stop for a while. So it's called the accreting and quiescence period. So that's really interesting because in the quiescence period, so when star is not accreting matter, we can actually observe X-ray emissions and we can model the temperature, the external temperature of the star. And with some observations, we can see how this temperature cools down. And this is really, really interesting because with this information, we can get some information on the composition of the core of the star. So in this plot here, you see representation of all the transiently occurring neutron stars that we know of. You can see that the arrows correspond to just like having upper limits in the luminosity and the accretion rate. But today we're talking about the source number 7 here, which you can see it has like a really good data point. So we have like the proper measurements for luminosity. You can also see on this plot that the luminosity we expect for this accretion rate, the luminosity we observe in the star for this accretion rate is like lower than we would expect. So in other words, this star has a very small luminosity. So this star is pretty much accreting, is like cooling very fast. So you can see this luminosity is not consistent with like slow processes, but it's consistent with fast processes. And we are not quite sure about which fast process is happening in this star, but we're going to talk a bit about this soon. So we know for sure this is a fast process happening there. So the star is really cooling very fast. Okay, specifically about the source, we have this paper here by Brown et al., which was the first paper to confirm that the star is really cooling very fast. And how they did it was not that they didn't use a specific equation of state or a specific superfluidity model. They just said, okay, based on this data and other possible simulations of how we can model the envelope around the star and so on, everything is consistent with the star cooling very fast, having very low luminosity than we would expect for this accretion rate. So our main goal in this research is really to reproduce this result, but now using the equation of state in a superfluidity model. So in other words, we have this data and we're trying to really compare with the models and see if we can rule out some models. So this is really exciting because this is the first data that we actually can use to do that. So how I'm going to do this, basically, as I said, there could be many processes that cool very fast in neutron stars. It could be pion emission, Kn emission, and so on. And this talk, we're going to focus on direct Wicker reactions, which are reactions that look like a beta decay. And I have here an example that shows like electrons and neutrinos of the electrons, but it could be muons as well. And the main point of this slide is just to show you that for those kind of equations, those kind of reactions to happen, we need to conserve energy momentum. So we need a minimum proton fraction of a star for it to be able to cool through this process, right? So as we also can see in equation 2, the calculation of this proton fraction is very much dependent on the equation of state that you use, which is included here in this parameter n. So those are the equations of state that we're using. There are the FSU-Gold family, and they are parameterized by this L parameter, which is the slope of the symmetry energy. So all these equations of state that you see here in the plots, they are virtually identical. They're obtained from RMF techniques. The only difference between them is really this L parameter, so the slope of the symmetry energy density, which is like another way of saying how we're modeling the dependence of the number of protons really in the star. Yeah, so this is how we're modeling the number of protons in the star. So you can see in the graph on the left, a massless radius plot for all the equations of state that we're studying. And in the graph on the right, which is my really main point of this slide, you can see how the L parameter is related to the proton fraction. So the bigger the L, the bigger the proton fraction that the star can reach. So this is really interesting. And we will see the consequences of this in a second. So yeah, those are the equations of state that we're using. And those are the models, the superfluidity, superconductivity models that we're using. So the problem of superfluidity and superconductivity is that they change, the predictions of those models change quite a lot depending on the immediate effects. And because we don't really have even theoretical techniques to calculate this precisely, there are several models that you can see here. So we decided to work with all of them and see what the different predictions they make, right? So let's say the unknowns here, the modelings, are the amplitude of this gap and the location where it begins and where it starts, where it begins and where it ends. Okay, and we're working with proton singlets and neutron triplets. So with all these ingredients, we can finally calculate some stuff. And I'm going to show you my results now. So the first thing that we do is to find the maximum mass stars that we can generate with this equation of state. So those two plots are basically the same thing. Plot on the left represents just like the mass of the stars that we generate with this equation of state. And the plot on the right just represents the central number density of the same star. So they're basically the same information, but just different quantities here displayed. So we can see that consistently for all equations of state, the maximum mass neutron star that we can generate something around 2.0 solar mass, corresponding to more or less 6.2, 6.3 central number density, 6.3 times saturation density of the central number density. So there's basically this curve here that I'm showing. Okay, so the next step is just to find the Dirac-Kurka threshold. So as I said, there is a minimum proton fraction that we need to reach to be able to cool the star through Dirac-Kurka emissions. And this is what this line represents. So everything above this line represents the region where Dirac-Kurka is allowed, and everything under this line is where Dirac-Kurka is not allowed. So this is the minimum proton fraction here. And you can see that for big L equations of state, this mass is very low. So pretty much what we're saying here is that all equations of state, all neutron stars can really go through Dirac-Kurka, which we know is not realistic. But on the other hand, if you have low L equations of state, then only high mass neutron stars can cool for Dirac-Kurka. So this is the scenario if we had no superfluidity. This has been studied before, but now I feel like the interesting thing is now what's going to happen when we put some superfluidity and superconductivity there. So some cases, for example, there is no difference. So as I said, there are many models, there are many different points of start and points of end and amplitudes of the gap model. So some of those models don't interfere at all. So you can see here, for example, everything under this line represents where the star is superfluid, and everything above this line is where it's not superfluid. So superfluidity changes the predictions for Dirac-Kurka because basically the free neutrons that will be able to generate, to interact through Dirac-Kurka reactions, if they're superfluid, they're no longer able to do that because they're now paired, right? So there's just like a smaller number of free neutrons available to cool through this reaction. So this means that whenever the star is superfluid, the Dirac-Kurka rates are very much suppressed. They're in fact exponentially suppressed. So we can say if the superfluid region of the star crosses this Dirac-Kurka allowed region, where it crosses, you'll see the significant reduction in Dirac-Kurka reactions. And this is what we see in the next plot here. So for this other gap model, which is called NTT, this whole region under this curve is superfluid. So this whole region that would in principle be allowed to cool for Dirac-Kurka, and it's now no longer doing that because like most of this region is superfluid. So the neutrons are paired, as I just explained. And then we have this prediction that now for this superfluid gap model, only high mass neutron stars will ever cool for Dirac-Kurka, regardless of the L parameter, regardless of the equation of state. So then you can see how strong the interference of superfluidity is in the predictions. And we also have like some other parameters that are like a bit crazy, like this one has a very different prediction just because the opening of the gap model happens later. So this region here is allowed to have Dirac-Kurka, but then superfluidity starts, so it's no longer allowed. And finally it ends. And this region where it ends here, up here, you can see that it's again allowed. So we have this funny prediction that for high L equations of state, low mass neutron stars can now cool through direct Kuruka, and sometimes in the extreme case, only low mass neutron stars can cool through direct Kuruka. Whereas if you have a low L equation of state, only high mass neutron stars can cool through direct Kuruka. So I know that's a lot of information, but it's just one final situation that can happen is that sometimes superfluidity happens in the whole star. So for example, in this case here, everything, even like high mass neutron stars, they're all superfluid. So we're basically saying that the whole core is superfluid. So this is a possible prediction for this GEP model. So how does this interfere on our calculation? So this is the point that we're finally comparing with data, right? So for this equation, for this specific neutron star, the MXP 165929, this paper by Brown said the luminosity of the star is something around 3 times 10 to the 27 joules per second. So we now calculate what is the mass of the neutron star able to generate this luminosity. So if there is no gap, then this is the curve. Those are the masses of stars able to generate this luminosity, which is interesting. But now let's see how this changes once we have superfluidity. So for this case, for example, where superfluidity doesn't interfere, we have the same prediction as expected. But for that other case, sorry about the bright yellow, again, as we expect, only high mass neutron stars are able to cool for direct Kuruka at all. So the mass corresponding to this luminosity is a high mass, something of the order of 1.7 solar mass neutron stars for all equations of state. And that other case, yes, and this is very much connected to the closing of the GEP model. So you can see here, I also plotted the dashed line, just the limit where the GEP model closes. And you can see that like as soon as the star is no longer superfluid, then direct Kuruka reactions already happen almost instantly. And then that's big enough to generate the luminosity we're looking for. And then we have this other case, it's also quite interesting. So again, for low L, for high L's, then we have like low mass neutron stars here generating the luminosity we're looking for. But for low L's, high mass neutron stars generating the luminosity. And then we have this plot that really shows all the possible predictions for all the GEP models. Something that you might notice is that usually, normally I had like 8 GEP models here, but in this plot you can only see 5. That's because 3 of the GEP models that we studied could not generate this luminosity. So in other words, with just 1 point of data, we're already able to rule out 3 superfluid GEP models to describe this data. So we know for sure that those 3 GEP models cannot generate the data, cannot reproduce the data. So this is the power of this framework of studying cooling and neutron stars. Just to finalize, I'm just going to say mention very briefly how we can also find more information about the core composition of the neutron star using this framework. So this plot is from a paper, from Brown's paper, and basically he's saying like, okay, we have this luminosity here that we measured, but if we're able to measure for the next 10 years, the rate of cooling of this star, and we're able to tell if it's like 1% or 2% or 4%, whatever, we can then also set some constraints on the heat capacity. And this is how we get like, even more information on the composition of the neutron stars. For example, in here, I have this like theoretical prediction, let's say, where they don't compare with any equations of state. And then in the right, I have the same plot, but now with our equations of state. So you can see that indeed, they have different, there's different predictions here. So this is the line for 1%, and this is line for 16%, corresponding to those lines here. And you can see that indeed, if we're able to measure this with like high precision, then we're also able to maybe set those 2 apart, including the GEP models. It's a bit crowded, but it's still possible. So hopefully I was able to convince you that this framework is really interesting. It's something that we should invest on, especially now that we have more cooling data coming from some sources. So I just mentioned here MXB 1659, where there's like 100 neutron stars, transiently accreting neutron stars that have been studied. So with more data coming from those kind of systems, we'll be able to set some constraints on the properties of the core of the neutron star and maybe shed some light on what's its composition. Thank you. Yeah, I have my email here if you want to send questions there. Thank you.
Thank you, Melissa, for this very nice talk. Let me just ask a question just to be sure that I understood correctly your result. So from what, if I'm not wrong, you are telling that there is a very interesting correlation between the value of L and the possibility of having the direct Urca. And if I'm not misunderstood, maybe I misunderstood, if L is larger than something as 60, 70 MeV, then what happens is something a little bit strange in the sense that the direct Urca you have at the level of neutron star with low mass, and vice versa if L is smaller than 60 or 70 MeV. Is it correct or I misunderstood?
Well, that is true, but only if we don't have superfluidity.
Okay.
Right. So let me just get one plate. So yeah, that's the case we're talking about here. Yes, if there is no superfluidity, then yes, then like high L equations of state, pretty much all equations of state could have direct cooling, but for low L, only high mass. So yeah. But then if you put superfluidity, then this picture changes. And this is, let's say, the danger of just studying neutron stars just from the point of view of the equation of state and not considering the superfluidity.
Right, thanks. Questions? Questions? Oh, Jonas, yeah, please.
Yes, Melissa, just wanted to understand something. How would things change based on that latest measurement of L, which turns out to be actually higher than before?
Yeah, so that's a great question. Thank you for that. So basically what this measurement tells us is that perhaps, right, there is some L here that is favored instead of like other L's. If we know for sure that this measurement is correct, then we could, for example, say, okay, so this part of the graph that is like lower, represents lower L can be ignored because like, we know that. But as I understand, we're not 100% sure, right? Because there's some tensions between gravitational wave predictions and, for example, nuclear experiments like PREX-2. So I understand this is a pretty much still open question. That's why we chose to consider like all L's.
Thank you.
Other questions? Okay, so I think it's very, very interesting what you are studying, because definitively the possibility of observing objects which are cooling not through the standard modified Urca puts a lot of constraints on the equation of state, as you were showing, and one can just hope that there will be even more examples of objects like that that will help us in modeling the composition of the star. So if there are no more questions, I thanks again, Melissa, and we can switch to Mikhail Beiger. Thanks.
Okay, hi everybody. Let me share the screen. Okay. All right. Can you see my screen?
Yeah.
Okay. So thank you very much for this opportunity to talk today. This is the talk on behalf of the LIGO Virgo Kagra collaboration and NICER collaboration. So this is, in my opinion, quite a nice example of multi-messenger work, collaboration between and with different channels of observations. So I will give a little bit of motivation first, and then I will talk about the results of this paper that is accepted, not printed in APJ, but you can have it on archive already. Okay, so moving on. So this is my kind of introductory slide of what we have in the field of gravitational waves currently. So this most simple taxonomy of gravitational wave sources can be viewed like that. We have either short duration sources or short duration in our detectors, because they may be a long duration in general, but what we see them as transients. So for example, binary systems. we know models of them very well. So this is GR modeled in spiral measure numerically, and then ring down also under control in the perturbation theory. Or we have like supernovae explosions or other types of bursts related, for example, to magnetar superbursts or cracks of crust or something like that, that are not so well modeled. So these are the short ones. And we have long ones, persistent or continuous waves that are coming, for example, from also binary systems, but also deformed rotating neutron stars. And this is basically the topic of my talk. Or it could be also a population of sources that is persistently emitting waves, and we are not very sure what. Well, so there are many models. So in some sense, we don't have a good model for this with the stochastic background. Okay, so today I will be talking about continuous waves from neutron stars. And so for those, we have, so basically these are the kind of few numbers or few facts that are important here. We have a source of gravitational waves that is long in time. So we need a long observational data span to detect them. So we didn't detect them yet, as you know, but they are possible to detect, and there are many possible models, possible mechanisms that can produce such a radiation. So this type of sources were already mentioned today. So they can be these so-called mountains on neutron stars sustained by elastic or magnetic stress, and we would have then gravitational wave radiation that is proportional to the rotation of the star. We can have oscillations like air modes. Then the proportionality is like that. We could have also free precession of a star or accretion processes that produce this deformation, this non-axis symmetry on the rotating star. That is, as you know, important, necessary to produce gravitational waves. So today I want to talk about R modes from neutron stars, and the R modes are basically kind of a spin-off idea of Rossby waves in planetary atmospheres. So that was discovered, that's first part of the previous century. And basically, the idea is that when we have a movement of air around the globe, the air is moving in different speeds at different latitudes, and then this movement together with the movement of the air creates such vortices. So we have such pockets or patterns of air moving like that. And on Earth we have so we observe this constantly, and for example use it for travel, because for example this jet streams in those latitudes the air is moving faster, so somewhere here and somewhere here. And then, for example, you can travel with the plane faster than usual. So this is an observed phenomenon, and R modes are Rossby waves. R mode waves are Rossby waves, but on neutron stars. So we don't talk we don't talk on neutron stars. We don't talk about jet stream, but we talk about such a pattern of movement of mass, a current motion. That has such a feature that the perturbation in a rotating frame, so in the frame connected to the rotating star, is moving in the way opposite to the rotation of the orientation of the star. So star rotates in this way, the pattern moves like that. But from the kind of observer point of view, from our detector point of view, the pattern moves in the same direction as the star rotates, which means that it takes away the energy of the star, and it also increases the instability. So because it's a sort of instability, so basically it's a kind of a self-driving instability. The driving force is the Coriolis force, and so long story short, but this is a potentially interesting instability that can first of all produce gravitational waves with a specific frequency and sustain itself given specific conditions, like for example that there is not too much damping and so on. This is an open question, but in principle. So we are basically in the observer frame, in the detector frame. We are expecting such a frequency of the gravitational wave in this lowest possible mode. Of course, this is a Newtonian approximation, so we have to take into account some corrections that are coming from GR that are basically, yeah, as you can see, they are proportional to the compactness and also other physical properties of the star. And this is very nicely summarized in this paper. So this authors produced nice feeds with many equations of state that are used in post-processing the results of this paper that I'm talking about today. So we have this theoretical idea of a R mode being active on the neutron star, and then the question is where we can have actual physical source that could emit such gravitational waves. And one of the good examples, or maybe one of the best examples, this pulsar. That is a young, energetic X-ray pulsar located in Large Magellanic Cloud, and that is called the Big Glitcher because it's amazing. And every time I look at this plot, I'm completely amazed because it glitches. This blue vertical lines represent the moments of the glitch. It glitches in a very regular way. It's almost like a pattern. And we think that. Not only we, but other authors too, that these glitches may induce R mode oscillations because the breaking index of the pulsar, because as you know, pulsars can be pulsar evolution in frequency can be described by the breaking index. The interglitch breaking index kind of tends to the value of n equal to 7. That, according to work of many authors, but recently Anderson et al. 2018, could describe an emission of gravitational waves by R modes, basically describe the spin down with n equal to 7 by emitting of R modes. So this is an interesting source to look at, because we have many moments in which the R modes can potentially be induced, and then we can study this interglitch periods for radiation of at this given frequency. So we have O3 data. This is LIGO Virgo O3 data that started here, ended here. In this time, thanks to NICER, we had very precise measurements of glitch times and also frequency derivative, and also the second spin derivative, a time derivative of frequency. And we have these 4 periods in which we can have a look at for gravitational waves at this specific frequency. Just one thing to mention is that this pulsar is associated with a supernova remnant, and we can kind of deduce an orientation of this pulsar. So I mean really physical orientation of the axis by looking at the supernova remnant. So assuming that supernova remnant has some symmetries, we can deduce the orientation, and it seems that this pulsar is actually, if it's true, it's oriented in the kind of less favorable way, in the sense that if it's oriented like that, then it actually radiates linearly the gravitational waves, which is the weakest orientation. So the wave emitted by the it's basically edge-on oriented towards us, not like pole-on, but edge-on. Well, this is just information for the next slide, because I will be mentioning about the different ways of looking at the data, analyzing the data, taking this information into account or not. Of course, we don't know exactly how it is oriented, but this is a good hint. I mean, looking at the supernova. Okay, so of course we don't know exactly the equation of state. This is what we want to know. So we don't know the parameters of the star. So we don't know how to relate the frequency that we observe in radio or X-rays with the unknown gravitational wave frequency. As you remember, this Idrisi et al. Fit requires some information from the equation of states to connect frequency of gravitational waves with the observed frequency in radio or X-ray. So we use this prescription of Caride et al. To connect frequency, rotation frequency and frequency derivative with the gravitational wave frequency derivatives, and so on. And the assumption here is that we connect it by parameters that are somehow fiducial, but assuming that they depend on the equation of state, but they don't really change between the glitches because they are the property of the star. And so having that, we can perform a search in gravitational waves, being kind of guided by the frequency parameters from the electromagnetic domain. So we use a few or two gravitational wave data analysis methods. Of course, in the paper, this is the main part of the paper. I will just mention it. Of course, that was the most labor-intensive work in the paper to analyze the data. The data is analyzed basically using some sort of a matched filter methods. We assume a model of the signal, and we then kind of filter out the signal from the noisy data. Basically, those two methods are matched filter methods, and they can be divided into two kinds. When we assume that we know the orientation of the pulsar, so this psi and iota, or not. So and then as you will see, this actually has some sort of an influence on the results that we have. So we analyze the data also in different ways from the point of view of how much data we take and analyze. So those information about the glitches times is important because we can divide the time in different ways. So these are this FG statistic used 4 periods divided like that, and 5 vector method, five segments of time. No, this is not very important. Okay, but the results, the upper limit, because we didn't detect the signal, but we got quite interesting upper limits that I will try to show. It's like that. We have these are the F statistic results and G statistic results for different time spans, and also five vector results. So this is when we assume the orientation. Here we don't assume an orientation of the pulsar, and also here. So this is without assumption of anything. This is a restricted parameter space. So this with the assuming the parameters, and they are kind of worse, as you can see. Also, probably because this radiation, when we assume it, is weaker because it's a linearly polarized wave there. Okay, so we don't have a detection, but we have an upper limit or upper limit. We can try to recover some information or try to compare it with the information that we may have from the astrophysics. So we can compare it with a bunch of equations of state, assuming that the star is actually emitting, so it's spinning down by the gravitational wave emission at this frequency that we are looking at. So we can then have a prediction of what the mass and moment of inertia can be for different equations of state. And basically, later on, I will be talking only about the two equations of state that are on the boundaries of this region. A very soft one, WFF1, and very stiff one. This is basically very artificial equation of state, causal equation of state, just plus the crust. So very stiff, very large radius. And basically, we can basically now play with these values to try to plot this, try to compare the amplitude that we got, the upper limits, with those functionals of equation of state that are different for different equations of state. So, for example, so those two black dashed lines are basically those limits that were shown before. This is an amplitude of the gravitational waves that we got, and these are the limits, as you can see from different methods. And basically, as you here see, these limits are already probing the amplitudes that are below the spin down limit. So the limit in which we assume that the whole spin down of the star is driven by gravitational wave emission. So we are really here probing a physical parameter space. Of course, most probably the star is not emitting, it's not slowing down by just purely gravitational wave emission. The amplitude is probably smaller, but we are now finally in this region of space in which we can really probe the physical space of parameters. So so basically, if the gravitational wave frequency is more than 90 Hertz, we are basically below the spin down limit here, which is quite interesting because we can now try to exclude or constrain things. So, for example, we can constrain the amplitude of the R mode, and of course this depends on the parameter of the star, and this is indicative of that probably the star is rather softer than stiffer, but of course this also depends on the mass of the star. So as we can see, these are the limits that were obtained by from the search, and these are this spin down limit for this equation state and this one. So so if the star is stiff, then the amplitude has to be much smaller than in this case. It's like that, and this could also be reformulated in a way of establishing or establishing a limit on the mass of the neutron star. So this also could be recasted in this way. We have an observational upper limits from the gravitational wave search, and then the mass constrained. So we could say that this kind of prefers the softer equations of state, and in specific regions even very small masses. So I would say that this is not a final word. I think I have to finish now. So this is my summary and outlook slide. I would have to say that this is not the final word, of course, but I think it's a very nice cliffhanger before the LIGO Virgo Kagra 04 observing run, and basically an open call to all the theorists to try their equation of state to compare with their results, because I think of course they will only be better in a year or so, and finally maybe next observing run will give us a much stricter upper limits or even a detection, and then we will be able to say something more about the R modes from this particular pulsar. So and of course I advise or welcome everybody to read the paper. Thank you very much.
Thank you, Mikhail. And questions, please. Questions. Jorge, Jorge's a question.
May I? Thank you. Thank you. Michael, if I understand correctly your conclusion, I mean, if the star will be spinning down only due to the R modes, the mass will be pretty small. So other way of saying this is that the star is not being spinning down by R modes, right? So why?
Yeah,
why
so the amplitude is probably smaller. Yes. It's so, because what we have just now probed is this most let's say optimistic or pessimistic, depending on how you look at it, scenario in which the observed spin down is because of the gravitational wave emission, but the amplitude can be smaller, of course.
Yes, why it should be spinning down only by gravitational waves?
No, it could, because of course the amplitude cannot be larger, so this is a kind of a meaningful limit, the spin down limit. It could, it probably is not, right? But it's a good kind of value that has to be compared with, right? So that we know that we are in the level of physical parameters, physically meaningful, right?
Yeah, so this is the limit when you equate the loss of energy with 100% gravitational waves. Right?
Yeah.
Okay.
Yeah. Yeah, because the amplitude cannot be larger, but it can be smaller, right? That's the thing.
If I'm not misunderstood, I mean the fact that the data seems to indicate that the breaking index goes towards 7, or n goes towards 7. If the mixture, I mean, if it is really breaking down as a mixture of gravitational waves and, let's say, a normal magnetic field, I am not 100% sure, would it really still go in the direction of n equal to 7 in that case?
Yeah, of course. There may be other ways of getting this n equal to 7.
There can be other ways of getting n equal to 7, not
I think
just
so, but yeah, I guess so. Yes, because the topology of the magnetic field there can be much more complicated than we think.
Okay.
But
other
well,
questions?
this is just what we can do. Sorry, so just
Yeah,
one sentence. This is what we can do from gravitational waves point of view, right? We are setting some limits on this model, which are already meaningful.
Yeah. Other questions? The questions? Of course, it's very, very interesting because the indication of an object which is small and as a mass as small as a radius, as you know, Mikhail, it's very, very stimulating for me and people working in our scheme. But of course, we cannot be too optimistic.
Yes. Yeah, but so this is my open question to everybody: how to explain this funny pattern? This is amazing. How does it work?
Yeah, that is also
just a question to know it.
Very okay, we have to move to next speaker. Thanks again, Mikhail. And
Thanks.
The next speaker is Jonas Pereira. And fine, please, Jonas.
I hope you guys can see my screen, right?
Yes.
Okay, so first of all, I'd like to thank the conveners of this session, Jorge and Alessandro, for the invitation. It's a pleasure to me to be here. And today I decided to talk about tidal deformations of hybrid stars with elastic phases and how this could be used to probe dense matter. This work has been done in collaboration with researchers from the University of Southampton and also Nicolaus Copernicus Center, where I work. If you want to have further details of what I'll talk about, please take a look at our published work. The strategy here is going to be simple. I will give the motivations for this study, then I'm gonna, sorry, just a second. I'm gonna give you a bird's eye view on tidal deformations of hybrid stars. I will say some words about elasticity in GR, which is important to characterize elastic hybrid stars. Then I will particularize things a bit, and I will talk about what can happen when the crust of a hybrid star is elastic, and I will gather the main points that I raised. Oh, sorry, okay. So what are the motivations for going beyond one phase perfect fluid stars? Or in other words, what are the motivations for talking about elastic stars with hybrid stars with elastic phases? It's basically twofold. On one side, we have the theory, QCD, which allows for phase transitions to deconfined quark matter, which is a fundamental ingredient for hybrid stars. And on the other side, we have observations in the sense that now we have the tools to assess such systems. For example, electromagnetically, we have a growing number of electromagnetic wave emissions, currently NICER, also EXTP, Athena, and the Strobe in the near future. And gravitational waves are also a reality now. and when they come from neutron stars, they can offer new observables, for example, tidal deformations, ellipticities, etc. I will focus here on tidal deformations. Also, from electromagnetic observations, we learn that neutron stars should be elastic, at least at certain densities, especially the outermost ones. This is important in order to explain the cooling curves of neutron stars. And also from gravitational waves, we learn that they could actually be hybrid. Of course, this is not definite. The case of GW170817 suggests this. It's not definite because the uncertainties are still large, but all of these things suggest that a reasonable way to go in terms of realism would be analyzing hybrid stars with elastic phases. And when one can learn actually a lot with this, because with better tools, we can not only probe but also constrain aspects to quark matter, which are so far very elusive on Earth-based laboratories. For example, the order of the phase transition and properties of the quark phase, for instance, if they are superconducting or even if they are crystalline. Another important thing when one moves ahead with more realistic models would be the proper understanding of the impact that the degrees of freedom have on observables. And here in particular, it would be due to phase transitions and also elasticity. This would be important because in the worst case scenario, they are important in order to characterize systematic uncertainties, which will be, of course, meaningful when we have more observations and more precise measurements. So I will focus here on one observable, which are tidal deformations. They are basically the result of the gravitational interaction of a companion onto a star, which has a finite size. It will deform the star, creating multipoles. And of course, their variation will lead to the production of gravitational waves that are of interest to us. And I will particularly focus on quadrupolar deformations, which are the leading order for gravitational waves. What is the description for tidal deformations? It's easier to do it in the early spiral phase because then the stars are far apart, and tidal interactions can be summarized as small quasi-static perturbations. In this case, the only thing one needs to do is to work with the theory of perturbations, having a background as reference. And here, for simplicity, we take a spherically symmetric one. And in the case of quasi-static perturbations and the spherically symmetric background, one can decompose perturbations in terms of spherical harmonics in the usual way. And for perfect fluids, one arrives at this master equation describing perturbations that once is solved, it characterizes all the other perturbation functions. But how to go from this to the values of quadrupolar deformations due to tidal interactions? This is obtained through the so-called love numbers, and it can be inferred in the weak field regime, where the TT metric component is generically expanded in terms of a quantity that's related to a point-like source, but plus a quantity that talks about its finite size and also the contribution coming from the external field. So I have put here their classical values, so you could have some intuition of what I'm talking about. For the tidal tensor, it is simply the derivative of the external gravitational field, whereas for the quadrupole tensor, it's the usual definition in terms of the mass density of the system. In order to infer the quadrupole moment, one should simply compare this generic asymptotic form with the external solution to the metric in terms of perturbations, and assume that the quadrupolar tensor is proportional to the tidal one. And from matching conditions of the internal to the external solution to the perturbations in a star, one can find the so-called love number, which is given here by equation 7. It is dependent on the compactness of the star and also on this quantity y. And this is exactly why one could obtain information about the properties of the star when this quantity is measured. And by the way, this quantity split by m to the 5th is a direct observable from the waveforms. That's why it's important. And from it, due to this dependence, one can not only extract information about the equation of state, but also on the stratification of the star, because this quantity y is also dependent on such aspects. How are things in the context of elasticity? Of course, they are more complex, and the first thing one needs to do is to generalize the classical theory into GR. This has been done by Carter and Quintana around 50 years ago. And in the simplest case where the background space-time is static, it is relaxed and perturbations are of first order, it's one can show that shear stresses, they enter in the formalism as corrections to the perfect fluid energy momentum tensor, and they are described totally geometric as here given by equation 9. And here you have the physical ingredient, which is the shear modulus of the elastic phase, which should be prescribed. For the fluid perturbations, one expands the components in the usual way in terms of the spherical harmonics and their derivatives. In the case where tidal deformations are taken as static perturbations for the Erlian spiral, the description is very much simplified because the only non-zero for velocity component is the time one. And the Lagrangian change of the metric is easily obtained by means of these fluid perturbations and the background space-time, which are all characterized. So it's actually easy to obtain all the shear strain components. In order to close the system of equations, one needs to give a barotropic equation of state, and it must be barotropic. The first law of thermodynamics should also be taken into account, and the law of baronial conservation should also be taken into account. In order to solve the equations, one also needs boundary conditions, and they are here related to the presence of any interface. In the case of hybrid stars with elastic phases, one has naturally the one coming from the phase transition itself, the quark to the hadron phase, but also in a given sector, for example, the hadronic interfaces from the liquid to the elastic phase. In each one of these surfaces, these conditions should be taken, which are basically related to the continuity of the tractions. That's important in order to avoid infinite gradients, and also the continuity of the extrinsic curvature components. These are important in order to guarantee that compositions of Einstein equations are also solutions to Einstein equations. When this is done for every interface in the system, of course, one should also take into account the boundary conditions for the fluid components, which are usually assumed to be continuous at each interface. When this is taken into account, one has a system of coupled ordinary differential equations. And because of the eigenvalue nature of this system, actually they are very, very restrictive. For example, in the simplest case of a perfect fluid hybrid star, with a sharp phase transition, there's a discontinuity of the energy density there, and this implies that the jump of h naught is the derivative of h naught is not zero, and this propagates out by means of y and influence tidal deformations. The question that I want to answer from now on is what would be the impact on tidal deformations when one also assumes an elastic phase. In order to try to answer this question, we have focused on some simple models, which basically cover different stiffnesses for the system. For the quark model, we have assumed a simple bag-like model with different speeds of sound. Also, the energy density jumps at the quark hadron interface are either free or fixed by some models, and And for the hadronic model, we have considered either very stiff equations of state, for example, NL3, or soft ones, such as SLY4. And we have also used this SH1 model, which is a bookkeeping equation of state, just to make sure that numerical integrations are fine. Here you have the mass radius relations for the equations of state I've mentioned previously with different jumps. And you see that indeed we're trying to cover different stiffnesses, because for a given mass, the radius range is significant. And for those who don't know, these cusps here are the critical masses and radii associated with the appearance of the quark phase, which is actually on the left of these curves. Now, I will particularize things, and I will assume that the only elastic part of the star is the crust, and its shear modulus is approximately 1% of its pressure. Here, I'm going to show some key results related to the changes with respect to perfect fluid hybrid stars. In this plot, you can see the dependence of the fractional tidal deformation change on the size of the elastic part. And when the latter is small, one sees that the departures from the perfect fluid counterpart are very small, of the order of 10 to -4. They are also dependent on equations of state, on stiffnesses, if you will. And all these curves here, they go to 0 when the size of the elastic part is 0. This is, of course, necessary, because in this case, one would be recovering the elastic fluid counterpart. However, changes may not be negligible and are of the order of a few percent in one particular generic case where the size of the elastic region is larger than half of the star's radius. So let me go now and wrap up everything that I tried to mention here. The elasticity might change tidal deformations up to the level of detections, which are the interesting ones to us, just when the elastic phase is considerable. Does it mean that elasticity is totally negligible in neutron stars? The answer is totally no, because there are many situations where this condition could be fulfilled. For example, when the quark phase is small and the density jumps are large enough, this could happen. Another possible scenario where this could happen is when there is a mixed phase, because it's also supposed to be elastic, or even in another case where the quark phase itself is elastic. By the way, it's already known in this case that tidal deformations could be very large. As a result of all the above, tidal deformations could also be probed to test these results. For the majority of them, it would only be possible with third generation gravitational wave detectors, but for the case of crystalline quark phase, it might be possible with the current ones. The future seems also very interesting because we will have higher precisions and more observations. And in this case, it would be very important to take into account elasticity and also properties of aspects of the phase transition, because in the worst case scenario, they might be relevant for the modeling of systematic uncertainties. Lastly, but not least, tidal deformations in the late spiral, which I have not mentioned, but I would just say some words about it, could also be important to constrain and to test aspects of dense matter, mainly related to their phase transition properties, because now, in this case, eigenmodes will also contribute to tidal deformations, and they carry with them all the information about each of the phases, as well as their particular aspects, such as transitions. So thank you very much.
Thank you, Jonas. Very nice talk, very interesting. Questions? I am very interested in this topic. You mentioned the possibility of a crystalline phase made of quarks. And have you already explored this possibility in your calculation, and what did you get in case?
Okay, this work, we haven't done this, but other people have done it. The one interesting name in this case is Lin from Hong Kong, and they have found indeed that using the expected values from the Loft phase, the fractional differences could be as large as 60%. We haven't checked these calculations yet, but they seem reasonable because they're in this crystalline quark phase, you'd have a humongous shear modulus, and it is the most interesting case where departures could be meaningful. But there are many technical problems there to be better thought, especially related to boundary conditions.
Yeah, thanks a lot. It's something very interesting. Maybe I will contact you later to discuss if you don't mind.
May I ask you something?
Sure.
Yeah. Yes.
Yes, about this point. So the calculation of the shear modulus. I mean, this is not being is not taken as an arbitrary parameter, but is being calculated microphysically.
Oh, in this that should be the self-consistent way of doing it. In our case, we have taken the result of certain fittings coming from the microscopic models, and for the crust, at least it's a good approximation to say they're around 1-2% of the pressure there. So it's a phenomenological model at this level, which is motivated by these microscopic fits.
Thanks.
Other questions? Okay. If there are no other questions, thanks again. And let's move to the last talk of today. David Barbara Gonzalez, that is also telling us about the elastic properties of neutron star crust. So please.
Okay, I will share now my screen. Are you able to see that?
Yeah, it's fine.
Okay, so let me change this. Okay, so thank you very much for having me in this session. My name is David Barba Gonzalez, and I am a PhD student at the University of Salamanca here in Spain. The topic of this talk is telling you about some properties of elastic properties of the neutron star crust, particularly the one component plasma approximation. So the contents of the talk will be the following. First, I will give you a brief introduction to the physics of neutron star crust, particularly within the framework of this one component plasma approximation. Then I will present you a feature that we have developed here in the context of molecular dynamic simulations, which is the Ewald summation for Gaussian charge densities under a debye potential. Then I will touch upon the subject that it is the most important one for our project because it is one of the main goals, which is the computation of some elastic properties via the understanding and studying of the stress tensor in a molecular dynamic simulations. Then I will present to you some preliminary results of the code that implements these Ewald summation features in it, to then finalize with the summary and conclusions of the talk. So we are here interested in the crust of a neutron star, which, as you know, is the outermost part of the object, going from densities ranging from 10 to the 4 to nuclear densities in the base of the crust. But here we're interested in modeling the outer crust, which the literature consensus says it's comprised of a Coulomb crystal, which has some sort of organized matter that is embedded in a degenerate electron gas that has two roles. The first one is making the system charge neutral, and the second one is screening the interaction between the ions that are degrees of freedom that we are using for our simulations, so that the interaction is governed by this debye potential, which is a screen Coulomb potential on the bottom left of the slide. And as you can see, when that lambda of Thomas Fermi that is in the exponent of the exponential goes to infinite, the debye potential goes to a Coulomb one. And this Thomas Fermi screening length is due to the electron screening produced by this degenerate electron gas that is embedding the crystal that is on the crust. When the crust of the neutron star cools down after the supernova that forms the object, the crystal is produced, and it can be produced in several composition characteristics. Here we are centering ourselves in the most idealized approximation, which is the one component plasma one, which assumes that the final state is composed of a single ion species with a single ion charge and a single ion mass number. Of course, in reality, these should be, at least the material should have some impurities, and even some people are considering it to be a multiple component plasma approximation. In terms of the distance to the center of the star, we are talking, of course, about the crust, which is in the outermost kilometer. And as I have said, the most important one to us here is the outer crust, because it is the Coulomb crystal with iron atoms. And of course, if you change the deepness, the depth in which you are on the crust of the neutron star, you will find some other ions that can be more neutron rich. But here we are focusing on this particular talk. I am focusing on the iron ions as the parts of this Coulomb crystal. So we are using, as I have mentioned, molecular dynamic simulations, which is, of course, as you may know, a semi-classical approach in which we integrate the equations of state of individual particles. And as I have mentioned, the individual degrees of freedom that we are using here are iron atoms, iron nuclei. We are not using nucleonic degrees of freedom for the integration of the equations of motion. And they interact with a screen-to-body electromagnetic interaction, this Coulomb screened potential by this exponential tail. For our one component plasma approximation, of course, we have to fix the ion charge, the ion density, and we fix the temperature. So that we are working on an MBT ensemble, because the number of particles, the volume of the simulation box, and the temperature are fixed. And we are able to control the temperature, the density, and of course, the lepton fraction via the nuclei mass number. One of the features that we are using here is the fact that we are using Gaussian charge densities instead of point-like particles. And the width of these Gaussian charge densities is controlled by this parameter A, which is the inverse squared width of the Gaussian distribution, and is measured, of course, in units of distance, inverse distance squared. Even though this Debye potential is screened, as I have mentioned, because of this exponential tail, depending on the value of lambda, there can be some long-range features, so that we are implementing a dual summation for this Debye potential and for the Gaussian charges. So we have our real charges here, which are the Gaussian charges that I have described just before. And the equal summation technique consists on the fact that we invent some screening charges that have the opposite charge as the real charges, which we want to simulate, but have different width. This parameter, this inverse squared width alpha equal, which is different than the one from the real charges. Of course, in order to maintain the physical reality of the system and the charge neutrality, you have to compensate. So you have to introduce the compensating charges that are on the same position as the real and screen charges, but have a positive charge. So having these real charges and these two invented charges, you have to divide, you can divide the interaction between the particles in three parts. A first one is a short range part which converges in the real space, because it is an interaction between the real particles and the real plus the screening particles, as you can see in this plot on the left side of the slide. For this short range part, we use periodic boundary conditions, as I have said, converges very rapidly with distance in the real space because of the screening of the particles. Then a long range part, that converges in the Fourier space, and there's the interaction between the real particles and the compensating charges, which are these ones with positive charge that exist in the same places as the real particles. And then you have to correct for a self-interaction that is interaction between the real particles and their own compensating charges that are on their same position. So the total interaction is composed of this short range part plus the long range part plus this correction for the self-interaction. The Coulomb E-Wald summation for Gaussian charges has already been developed in the literature, and you may find that it has a closed form in terms of these complementary error functions. And we found that the calculation of the same interactions, in this case the short range interactions, but for the bipotential, gives rise to non-analytical integrals that we have to numerically integrate every step. So it is this integral here with an hyperbolic sign, some exponential terms, and this potential here that I display on the bottom part, which is the Debye potential produced by the sum of a real charge plus a screening charge. As you can see, both the inverse width, squared width of the real and the screening particles are involved here. Then to delve deeper into the comparison between the E-Wald frameworks between Coulomb and Debye, you can see here it is the short range interaction that I just mentioned. You have also for the self interaction these non-analytical integrals that you have to integrate numerically every step of the way. And then you have the long range Fourier interaction, which is quite the same as for the Coulomb part, but with this term here correcting for the lambda of the Thomas Fermi lambda. Now I want to briefly touch upon the subject that I've mentioned is the main goal of the project. We are right now working in it, but we have not quite the results to show you yet, which is the elastic properties of this material that we are investigating, this neutron cross material within the one component plasma approximation. So we want to do that through the stress tensor, which is a set of quantities that describe the state of internal forces that the particles within the simulation box are feeling and exerting on each other. It is a set of quantities that is measured in the units of pressure, and its importance for the in terms of its usefulness to understand the elastic properties of the material is the fact that its value, the value of the components of this matrix, which is a stress tensor, is sensible to the deformations of the system. You can see here a figure taken from Kaplan and a letter by Kaplan and collaborators in 2018, in which they performed a molecular dynamic simulation, but in this case for a state of matter which is nuclear pasta, which is at the base of the crust, and they plotted here the stress, some of the components of the stress. These, for example, in the left part of the plot, you can find the diagonal components of the stress versus this parameter, which has to do with the deformation of the molecular dynamic simulation box. And you can see that the value of the stress component changes when the system is deformed. That is the important point. And if you can show that the system is linearly elastic, then, if you can show that the system is linearly elastic, then you will be able to apply this generalized Hooke law, in which you will have this epsilon, which is the matrix of deformation that has something to do, of course, with these epsilon here, which are the deformation that Kaplan and collaborators used. This sigma is the stress tensor, and this 4-ranked tensor here, C, is what is called the elastic moduli tensor, and it is in particular for us, it is the main goal to obtain this elastic moduli tensors for the one component plasma approximation of the iron phase of the neutron star crust. They are important. We are still investigating this, so I cannot delve deeper than I am doing now into the details of this part of our work. But we are trying to understand the relationship between these quantities, these elastic constants, to the shear modulus of the crust of the neutron star, and of course the effect it can have in potential gravitational wave signals. So now that I have talked to you about the new features that we have implemented in these molecular dynamics codes and our final goals, I want to show you some preliminary results of the molecular dynamics codes. I have chosen 3 representative examples of what I find interesting about the topics that I have talked to you before. The first one is the Coulomb limit. As I have mentioned before, this is a potential which when the Thomas Fermi screening length lambda goes to infinite, it is exactly the same as the Coulomb potential because this exponential goes to 1, sorry. So that you would expect that the results of a Coulomb code, of a molecular dynamics Coulomb code with E-Wald summation of course, and our code with this potential here. When lambda tends to infinite, should go inside. And as you can see in this graphic, in this plot, I am showing the total energy per nucleon for a RAM with 10 ions and this density against simulation time. And as you can see, very rapidly, the two systems, the Coulomb one and the dy one with lambda tending to infinite, they converge to the same total energy. And another feature that is important to mention from this plot that I am showing you is the effect of the electron screening in the total energy, which in this case is of course less. This electron screening effect is less effective when lambda is larger, and is more effective when it's smaller. And the effect it has on the system is that it makes it less bound than in the Coulomb case. As you can see here, when lambda grows, the system is more bound, the energy is more negative up to the point when it reaches the Coulomb state. That is the limit when lambda tends to infinite. The second example that I wanted to show you, it is a very important one, which is the convergence of the Ewald summation. What I mean by the Ewald summation is this summation here on the bottom left, bottom right part of the slide, the summation over K. Those K are the reciprocal lattice vectors of the imagined lattice that the infinite images of the simulation box spanning over all direction form. So those K's are the reciprocal lattice vectors of that imagined cubic lattice. And I might remember you that this alpha Ewald parameter, it's the width of the screening and compensating charges, so that it is not a physical quantity but a mathematical artifact. One of the bases of the Ewald summation is the fact that this sum has to converge because of this exponential to the minus k squared and this 1 over k squared. And you can see here for another run in which I plot the total energy per nucleon against this parameter alpha Ewald, that the larger the number of terms that you include in this summation over k, the number of reciprocal lattice vectors that you include in the summation, the better the Ewald summation converges. This is for, of course, for the dy potential and these particular characteristics of the sample. And the point being here is that not only it converges, but it makes so it converges to the same value independently of alpha Ewald. This is something to be expected, and it is a good result that shows somewhat the consistency of the code, because as I have mentioned before, physical results such as the energy per nucleon should not depend on alpha Ewald because it is a manufactured parameter. And this non-dependence of alpha Ewald happens, but only if you are well into the convergence phase of the summation of over the reciprocal lattice vectors. This is simply a zoom into this region of the previous plot, so that you can see the behavior of the convergence in terms of this parameter, this inverse squared width of the compensating and screening charges. Last of the results, I wanted to show you one particular example of the kind of results that we are obtaining for the distribution of the particles within the simulation box. Of course, it is known that the phase of matter that exists on this Coulomb crystal is an ordered state. So it is important that we are able to find the range of densities and temperatures in which our system thermalizes into an ordered state, in this case, for an example, with a temperature of 1 MeV, and the density here, ionic density always 0.017 and 15 particles. We are finding an ordered state with this. It is this snapshot and then this pair correlation function GFR versus the normalized distance, normalized based on the simulation box length. Of course, we are always talking, we are still not deforming the simulation box, so we are using a cubic simulation box. So I jump now to the summary and conclusions of this talk. We have developed a molecular dynamics code that is able to simulate neutron star crusts in this one component plasma approximation. This code, being a molecular dynamics code in which you can change the potential, is also suitable to implement other semi-classical potential, in particular those that are short range and do not need the work to develop the Ewald summation for them, such as the hadronic potential that makes that is used in the simulations of nuclear pasta. We have introduced this Ewald summation for the dBi potential that accounts for the electron screening, and I have shown you that it offers good results in terms of the Ewald convergence and non-dependent on the width of the screening particles, and in the Coulomb limit comparing to a Coulomb Ewald code. Our goal that we are working on it right now is to study the elastic properties of this material, computing those elastic constants and by varying the stress tensor for different deformations. We have an eye on the effect of this in the gravitational wave signals. As I have mentioned, this is something we have to investigate further. And I thank you very much for your attention and for the invitation to this session. And I am now open to your questions. Thank you very much.
Thank you for the very interesting talk. I see already a question by Jonas Breck, please.
Yes, thank you, David. I just wanted to ask something. It's probably not what you've done, but I just wanted to hear your insights about it. And the question is this: is the formalism that you have presented also valid for the pasta phase?
For the pasta phase produced by, of course, the Coulomb interaction and the short range hadronic interaction. So for the Coulomb interaction, of course, our framework with the Ewald summation is also valid, but you'd have to add this hadronic potential. The fact is that if you add this hadronic potential, it is very short range, so that you would not need to implement the Ewald summation. So our code is suitable to add on it the hadronic potential and try to change the conditions of the density, the masses, and the charges of the particles so that you can simulate other phases of the crust, such as the pasta phases.
But wouldn't the shapes there in the pasta phase be a problem? Are they important in what you do?
In terms of the framework, as I've mentioned, of the Ewald summation that I have mentioned, I think that is not important. What it would be, we are studying and we are using these results that are on the letter of Kalman and collaborators. It would be important also to understand the elastic properties of the pasta and whether the calculation of the stress and the elastic constant would be applicable to the nuclear pasta. But for the case of the molecular simply of the interactions and the Ewald summation for the hadronic and the Coulomb potential, it would be applicable to the pasta phases. Yes, I think so.
Okay, thank you.
Other questions? Okay, probably people also are thinking about lunch. Okay, there are no further question. Jorge, maybe we can close this session, and we have to remind people that tomorrow at 4:30, isn't it? We have a second.
Yes, half past 4 p.m. we have the second half of the session. So all of you are welcome to participate. So we're looking very much forward to seeing all of you tomorrow, to meet you again. This was an extremely interesting session. I'm very happy with how we are a bit late, but that was so interesting that it's okay. So we'll meet you again tomorrow afternoon. So
yep.
Thank you very much for your participation.
Thanks everybody. And
thank you. Bye.
Thank you. Bye.
Bye.
See you tomorrow.
Thank you, guys. See you.
Bye. Bye.
Ciao. Hey, Matthias. Ciao. Nicolas. Ciao.
Hi, nice to see you.
Nice to see you, Matthias. Nice to see you. Oh my God, you have a portrait of a goat.
Oh, yes, here.
Nice.
Yeah, Alessandro,
yes.
I will speak tomorrow, give my talk in your session.
Yes.
I have a little bit of problem because I have another talk in a parallel session also. So I have to, I cannot be all the time in your session. Yeah, so.
Don't worry,
yeah.
we are all having problems similar to that. So I also had to switch for half an hour to another session.
I heard your talk, I think it was on Monday. And I'm really surprised that now with the new data from NISA, your model looks really good, I have to say.
Thanks a lot. Thanks a lot. But the talk today talk of Michael Baker was suggesting something that is even more interesting, because he's suggesting that maybe there are also objects with a very small mass and very small radii. That of course we would be extremely happy, but you know, I always think that we are wrong. We cannot be right. It's impossible. Okay, so see you tomorrow. See you tomorrow.
See you tomorrow.
Ciao,
Bye bye
Mattia.
bye guys.
Ciao,
Ciao ciao, grazie Alessandro. Ciao ciao.
ciao, grazie a te. Ciao, 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 ciao.